Welcome to HeapLAB Part 1. My name's Max, and I'm here to take the mystery out of heap exploitation. It's something that hackers have been doing for over 20 years, starting with the first publicly documented heap exploit in 1998. This is an interactive course, so you'll need a Linux host or VM to get the most out of it. We'll be setting that up later. We'll start by learning what GLIBC is, what a heap is, and how the two are associated. Then we'll set up our environment and dive straight into our first heap exploitation technique, known as the House of Force. For every technique that we learn, we'll start by understanding the heap internals required to figure it out. Then we'll move on to turning that technique into an arbitrary write primitive. And finally, we'll drop a shell using our heap exploitation techniques. Along the way, you'll face two challenge binaries from which you're expected to drop a shell using what you've learned so far. It is technically demanding with a lot to learn, so don't hesitate to rewind videos and watch them more than once until you're comfortable with each technique. So if you're a capture the flag player, exploit developer, or just interested in weird machines, then this course is for you. If you're ready, I'll see you in the next video. For those of you unfamiliar with it, GLIBC stands for the GNU C library. It's an open source library that takes the form of a shared object, the Linux equivalent of a DLL, and it's a fundamental part of many Linux operating systems. Alternative C library implementations exist, such as Muscle and UCLibc, but GLIBC has been around for the past 30 years and is widely adopted. It's used in both desktop and embedded systems, including popular distros like Ubuntu, Debian, and Arch Linux, to name just a few. And all GLIBC does is provide boilerplate code, functions like memcopy and printf, to programs written in C and C++, and by extension higher level languages like Python, whose interpreters are often written in C. Put simply, on your average Linux distro, you'd be hard pushed to find a process that doesn't map one of the GLIBC shared objects into memory. On your screen now is an Ubuntu 18.04 long-term support distro, which I'm going to use to demonstrate where to find an operating system's GLIBC shared objects and how important those shared objects are. There's no need to follow along at this stage. We'll be preparing our environment soon. LDD, short for List Dynamic Dependencies, lists the shared objects that a binary relies upon. Running it against ls shows that ls loads libraries such as libse Linux and libpthread. Amongst these libraries is one named libc.so.6. This is the GLIBC shared object. GLIBC is often shortened to libc, and the .so part stands for shared object. The 6 part is part of the Linux library ABI versioning convention known as a soname. A library maintainer increments their library's soname when its ABI changes. File shows us that libc.so.6 is just a symbolic link to libc-2.27.so. This is the actual GLIBC shared object. 2.27 indicates the GLIBC version, which is different to the soname. Most Linux operating systems are distributed with a specific version of GLIBC, which often will not change for its support period. For example, we've seen that Ubuntu 18.04 long-term support uses GLIBC version 2.27. It was created with this version and will continue to use it throughout its 5-year support period. The exceptions to this rule are rolling distros like Arch Linux, which do update their versions of GLIBC. Running file on the actual GLIBC binary reveals that it's just a position-independent ELF file, much like how Windows DLLs are PE files. The build ID can be used to identify a specific build of GLIBC. We can run the GLIBC shared object, and it will print information such as its version number and what version of GCC it was compiled with. If you're unsure of which version of GLIBC you're dealing with, running the shared object is a quick way to find out. DU, short for disk usage, shows us that the libc binary takes up just 2 megabytes of space on disk. So how important are these 2 megabytes? Well, I'm going to remove them and find out. This command deletes the libc.so.6 symlink. Now when I try to use simple programs such as ls or whoami, they're unable to run. Closing the terminal emulator makes it unresponsive, programs like Firefox won't start, and the OS can't even shut down. That's how important GLIBC is to the integrity of a modern Linux operating system. So in summary, GLIBC is a shared object or library that provides boilerplate code to nearly every process on the operating systems that use it. And it's so integral a part of these operating systems that even their most basic functionality requires it. In the next video, we'll learn about heaps and how they're related to GLIBC. Included in the boilerplate code that GLIBC provides is a dynamic memory allocator, known as malloc. Dynamic memory allocators are used when a program can't know the size or number of objects it needs prior to runtime. And malloc's job is simply to dish out so-called chunks of this dynamic memory to processes at runtime. And those chunks come from large contiguous regions of memory known as heaps. There's nothing special about heap memory. They are simply large contiguous blocks of memory that malloc requests from the kernel. If you've ever dealt with strings in C, you've almost certainly used malloc. In C++, you're a little more abstracted. The new and delete operators are thin wrappers around malloc, as are, by extension, make shared and make unique, etc. Even if your code doesn't explicitly invoke malloc, chances are one of the library functions you're using does. Basic operations like starting a new thread, opening a file, or dealing with I/O all use malloc under the hood. So the fact that malloc is so widely used, combined with the fact that it's used in languages like C and C++, for which memory corruption is still an issue, both make it a great target for exploitation. And that's what we're doing throughout the course. Now, I mentioned the first publicly disclosed heap exploit was in 1998, but all that involved was overwriting some user data on the heap. And overwriting, for example, a function pointer on the heap via an overflow is no different to doing the same thing on the stack or elsewhere. We're going to focus on so-called generic heap exploitation techniques that, to the greatest extent possible, leverage malloc's internal operations against itself. The idea being that once you've learned a technique, if you find a heap-related bug in a program that fits the constraints of that technique, you could use it for an info leak, denial of service, or even arbitrary code execution. To summarize, programs can use the malloc memory allocator at runtime to request chunks of heap memory, which is no different to any other type of memory. Malloc is used nearly everywhere, and we're going to learn how to exploit it. In the next video, we'll set up our environment. Before we start learning the different heap exploitation techniques, we need to set up our exploit dev environment. If you have some exploit dev experience and want to use an existing environment, you can do that too. If you don't, the first thing we'll need is a 64-bit Linux host or virtual machine. I recommend using a recent Ubuntu desktop build, since not only is Ubuntu the platform that our tools were designed for, it's also free and works out of the box. You can get the latest Ubuntu desktop image by visiting ubuntu.com and clicking the Download tab at the top of the page. I'll be working from the Intel x86 architecture for the duration of this course, but the techniques we'll learn are grounded in how the C library works, so for the most part, they're architecture agnostic. You can install Ubuntu on your host or create a new virtual machine. I'll be using an Ubuntu 18.04 VM, virtualized under VMware because it has a very convenient easy install feature. If you're using a different virtualization suite, for example VirtualBox, you may need to take some extra steps, such as installing VirtualBox guest editions to ensure that your VM supports features like copy-paste between host and guest and can be run in full screen. Once your Linux desktop is up and running, you'll need to install a couple of tools. The first of which is a Python framework called pwntools. You can find its GitHub page at github.com/gallopsled/pwntools, where simple installation steps are detailed. Pwntools is primarily a capture the flag framework, but it's great for rapid prototyping during exploit development, and we're going to use it to help script our exploits. The second tool we need is an enhancement suite for the GNU debugger, or GDB. GDB isn't particularly user-friendly or exploit development focused, which is why we're installing a GDB Python library called pwndbg. It can be found at github.com/pwndbg/pwndbg, along with its simple installation guide. Pwndbg makes GDB a lot more user-friendly, and more importantly, has some great heap introspection functionality. Installing pwndbg will install GDB, so there's no need to download it separately. If your version of pwndbg ends up being more recent than the one I'm using, the output of some of the commands may appear slightly different. The third tool is something called a OneGadget finder, which we'll learn about later. The GitHub page is github.com/david942j/OneGadget. Note that it requires the installation of Ruby first. Once you've got everything installed, you need to copy the heaplab.tar.gzip file included in this section's resources into your environment. You can download it directly, or if you're working inside a VM, copy it across via a shared folder or shared clipboard. Extract the archive with the command tar xzf, followed by the name of the archive. You can extract it anywhere you like, as long as its internal directory structure remains intact. The archive contains everything we need to begin. There's also a PDF that serves as a reference guide for malloc internals and contains an overview of each heap exploitation technique we'll be learning. A separate copy of the PDF is also supplied in this section's resources in case you want to browse it outside of your environment. Each directory contains a vulnerable binary against which we'll leverage a different heap exploitation technique. Most of them involve guided learning, whilst some are challenges that you'll approach on your own. Lastly, go ahead and install a text editor of your choice. We'll need it to edit our exploit scripts. I'll be using Vim, but graphical editors like Atom or even an IDE like PyCharm will work just fine. And that's all you need. Now that your environment is set up, we're going to start learning how malloc works under the hood. We're going to learn the malloc internals required to understand our first heap exploitation technique, the house of force. Now, malloc is just a collection of functions and metadata for the purpose of dishing out those chunks of heap memory to processes. And today we're concerned with just two of those functions. The malloc function for requesting heap memory and the free function for recycling it. Yes, it is a little confusing to have a function called malloc used to request heap memory from the dynamic memory allocator, also called malloc. But at least it's a simple function. It takes a single argument, the size in bytes of memory that you want, and it returns a pointer to that amount of memory or slightly more for you to do with as you wish. And to help us visualize how heap memory is requested via malloc, we're going to debug a small demo binary. Working within your exploit dev environment, open a terminal and navigate to the HeapLAB folder you downloaded earlier, then to the House of Force directory. in which you'll see a collection of binaries and scripts. We're going to debug the demo binary under GDB with the command gdb demo. Once GDB has launched, we'll set a breakpoint on the main function with the command break main, which can be shortened to bmain. Then we'll run the target binary with run or just R. Welcome to pwndbg. There's a lot going on screen, but right now we're only concerned with the source panel, third from the bottom. To stop pwndbg printing all this other information every time we step through the source code, we'll issue the set context-sections code command, which restricts future output to just source code. For the rest of the debugging session, if you want to print the source panel, you can use the context command. In the source panel, we can see that all this program does is request some heap memory using the malloc function several times, starting with this first request for 9 bytes, where it saves the return value in a variable called A. But before we let the program do that, let's take a look at the heap. The vmmap command prints a memory map for this process, and from the legend at the top, we can see that the heap should be colored blue. But there's no blue text in the command's output. This is because malloc won't request memory from the kernel to form a heap until it needs it. So go ahead and use the next command, which can be shortened to n, to execute that first request to malloc for 9 bytes. Pwndbg shows us that execution has progressed to line 7, now printed in bold and indicated by this arrow. Now the output of the vmmap command shows us that we have a heap at address 602000 with a size of hex 21000 bytes. That's just over 135,000 bytes. Note that this video was captured on an Ubuntu 18.04 VM. If you're using a different OS or running on bare metal, these values may differ. Next, we'll inspect this heap memory using the viz heap chunks command, which can be shortened to viz. If your output looks different to mine, not to worry, you may be using different terminal color settings. In my case, the region colored cyan is the chunk returned from that first request to malloc for 9 bytes. This can be confirmed by typing print A or PA, which shows us that the return value from that call points here to the first quad word of this chunk's so-called user data. The first thing you'll notice is that we got more than 9 bytes. 3 quad words at 24 bytes, to be precise. It turns out that this is the minimum chunk size that malloc will provide you with. If we use the next command to request just 1 byte, viz shows us that malloc still returns a minimum sized chunk. Even when the program requests 0 bytes with the next command, viz reveals that it was still issued with the minimum chunk size, with 24 bytes of user data. You may be wondering what this field here is, before this first chunk's user data, but still part of the same chunk. Well, malloc uses so-called inline metadata, meaning that much like how stack metadata, such as saved base pointers and return addresses, are stored on the stack itself, malloc stores some of its heap metadata on the heap. Specifically, in this case, a size field. Every chunk has a size field, indicating the sum total of bytes that make up the chunk, including the size field itself. So, in the case of these chunks, 24 bytes of user data plus 8 bytes of size field makes 32 or hex 20 bytes. However, we're seeing a hex 21 value here. That's because malloc's chunk sizes increase in increments of 16 bytes. For example, if we use next to request exactly 24 bytes of heap memory, viz shows us that we were allocated a hex 20 sized chunk with exactly 24 bytes of user data. Now, if we use next again to request 25 bytes of heap memory, viz indicates that this time we got the next chunk size up hex 30 with 40 bytes of user data.
Because the least significant nibble of each size field isn't used to represent chunk size, it's instead used to represent flags. In this case, the least significant bit is set, indicating the prev in use flag. The prev in use flag simply means that the previous chunk, the adjacent chunk in lower memory, is being used by the program. Since all of these chunks are in use, all their prev in use flags are set. The first chunk's prev in use flag will always be set because it has no previous chunk. If you want to review information about chunk flags, you can find it in the chunks section of the PDF. You might also be asking, why doesn't the first chunk start here, at the beginning of this memory map, leaving us with this offset pattern? Well, technically it does. Malloc considers chunks to start 16 bytes before their user data. So from Malloc's perspective, the first chunk does start there. When our program is dealing with chunks, we'll see pointers to a chunk's user data. But when malloc gets hold of those chunks, we'll start seeing addresses 16 bytes lower. To add another layer of confusion, malloc chunk shapes, at least when viewed like this, are variable and depend on a couple of factors, including the size of the chunk, the size of the previous chunk, and whether either or both of those chunks are free. We'll get to free chunks later. Fortunately for our first two techniques, we're only going to see chunks shaped like these. Lastly, I'd like to draw your attention to this region, labelled the top chunk. You'll recall from the output of our vmmap command earlier that this heap is about 135,000 bytes long, but we're only seeing a couple of hundred bytes here at most. Malloc treats that remaining as yet unused heap memory as a single large chunk, known as the top chunk. It's called the top chunk even though when viewing memory from low to high addresses, it appears as though it's the bottom chunk. It's the top chunk in terms of residing at the highest address. Every time we've requested heap memory via the malloc function, malloc has broken off a piece of this heap's top chunk, given it a size field, and handed us a pointer to its user data. And if we keep requesting chunks like this, malloc will keep taking them from the top chunk until there's not enough memory in the top chunk to service our request, at which point malloc will attempt to extend the top chunk. And to keep track of whether a top chunk is large enough to service a request, it also gets a size field, which we can see here. And interestingly enough, in many versions of GLIBC, top chunk size fields are not subject to any integrity checks. And this forms the basis of the house of force. You can close GDB with the quit command or Control-D, and in the next video, we'll take a look at our first vulnerable binary and see how we might leverage what we've learned so far about malloc to exploit it.
In this video, we'll take on our first vulnerable binary, and we're going to use it to learn our first heap exploitation technique known as the house of force.
It was first documented in 2005 in a paper titled The Malloc Maleficarum, which was considered the GLIBC heap exploitation Bible for some time. The author, who goes by the handle Phantasmal Phantasmagoria, developed 5 generic heap exploitation techniques that they named the houses of prime, mind, force, law, and spirit. Since then, many techniques have followed the same house of naming convention. So let's dive straight into the house of force. If you're not still in the house of force directory, navigate back there now. Our first vulnerable binary is the one named, fittingly, house of force. It's a small CTF-style binary written in C. It has a heap bug, against which we're going to leverage the house of force technique. Whenever we encounter a vulnerable binary, we can learn about its security stance with the checksec feature installed with pwntools. This binary is 64-bit, as are all of our vulnerable binaries. It's compiled with full rel-row, which again is the case with all these binaries. Partial rel-row is an exploit mitigation that changes a program's section layout in memory, and full rel-row also maps some of those sections as read-only after initialization. Since our exploitation attempts focused primarily on GLIBC rather than the individual binaries, this won't be an issue for us. This binary was also compiled with NX, also known as dep, amongst other names. This is the case for all our binaries except one. NX is another exploit mitigation that enforces whether pages of memory can be treated as executable code. PI stands for Position Independent Executable. This binary is not position independent, which means at runtime, we'll know its address. This is just so that we have a static location where we can target our arbitrary writes. The binary is otherwise subject to ASLR, or Address Space Layout Randomization, meaning that its stack, heap, and libraries will be loaded at random addresses. The challenge binaries, however, are all position independent. Lastly, a run path value like this would normally be a security concern, because it means that this binary will go searching for important libraries, like GLIBC, in a directory that the user controls. All our binaries have a modified run path, because it's the easiest way to link them against different versions of GLIBC. A non-standard run path is not something required for heap exploitation. Let's familiarize ourselves with the vulnerable binary. Loading it into GDB with the command gdb house of force will allow us to inspect the process's heap at runtime. We'll run the binary without setting any breakpoints with the run command. The program displays its title, followed by two addresses. The first is the address of the putS function within glibc, from which we can extrapolate glibc's load address. The second is the start address of this process's first heap. So much for ASLR. Leaking both heap and glibc addresses is possible via heap corruption, and rest assured that at least one of our challenge binaries won't be so forthcoming. However, when learning a new technique, the vulnerable binaries will leak any addresses we need so that we can focus on the technique at hand. Below the leaked addresses is a numbered menu. Option 1 allows us to request up to 4 chunks of heap memory via the malloc function. We're prompted for the amount of memory that we want. I'm going to request 24 bytes. Then we're asked for any data we want to write into that memory. I'll send some capital Ys. There's no pretense that these binaries are anything more than a direct interface with malloc. It allows us to learn the techniques without getting bogged down by peripheral functionality. Just remember that getting malloc to do exactly what we want is often not as simple in a production environment. Now that this process has a heap, let's take a look at what state it's in. You can break in GDB with Ctrl+C, then visualize the heap like we did before with the viz command. If you need a reminder about which pwndbg commands are available, you can type pwndbg to list all available commands, or follow it with a search term. We can see that this heap starts at address hex 603000. When a process is started under GDB, ASLR is disabled, so this heap will always start here when we debug like this. As expected, malloc has allocated a hex 20 sized chunk with 24 bytes of user data to fulfill our request for 24 bytes. The same sized chunk would have been allocated had I requested anywhere between 0 and 24 bytes. We can see that the program has written the data we sent it into this chunk, starting at the beginning of its user data, 4 capital Ys and a new line represented by their character codes in hexadecimal here. So this program lets us request arbitrarily sized chunks of heap memory and fill them with data. Let's explore the rest of this binary by issuing the continue command, which can be shortened to C. At this point, we can hit return, and the program will print its menu again. Option 2 prints the target. I mentioned that the first thing we would do after learning a heap exploitation technique was turn it into an arbitrary write primitive. And our objective is to use that primitive to overwrite the target data, which is a short string of capital X's that reside in this binary's data section. You'll recall that this binary is non-position independent, so we always know the address of the target data. We can check on the target in memory by breaking with Ctrl+C, then issuing the dq or dump quad word command, which shows us those capital X's represented by these hex 58 bytes at address 602010. Option 2 is just a quick way to check if we've successfully overwritten the target. If you're ever unsure of which mapping a specific address resides at, the xinfo command can help, used here to confirm that the target data is indeed part of this binary's data section. Continue, followed by return, shows us that the third option just quits the binary. So once this video ends, familiarize yourself with the vulnerable House of Force binary and see if you can find the bug. There's no need to go digging through the assembly. This is not a reverse engineering course. You could try, for example, using option 1 to request some heap memory, then send the program more data than it's expecting. Once you're comfortable with how the binary works, join me in the next video where I'll explain this program's bug, then we'll exploit it together. Did you find the bug? If you did, great. If not, don't worry. This isn't a bug hunting course either. I can tell you that the House of Force binary has an overflow bug when receiving the data it writes onto the heap. Let's confirm this. Load the House of Force binary into GDB, just like we did before, and start it with the run command. Use option 1 to request some heap memory. I'm going to request a minimum sized chunk to keep things compact, but you can request any size you like. Then, when prompted for data, send more than the amount of user data your chunk has available. For example, my request for 24 bytes will yield a 20 sized chunk with 24 bytes of user data, so I'll send more than 24 bytes by spamming a load of capital Y's, because why let the capital A's have all the fun? Now let's break in GDB with Ctrl+C and inspect the heap with viz. We can see that malloc has allocated a 20 sized chunk as expected, and the program wrote our capital Y's into that chunk's user data. But we can see that 8 bytes of our input has overflowed the chunk. Not only that, our data has overwritten the top chunk size field. So this binary has an 8-byte overflow when reading data into chunks. Is that a realistic bug? Perhaps. It could just as easily have been a off-by-1 error in an array of long integers, for example. The point is that even a single byte overflow can corrupt the size field of the succeeding chunk, including that of the top chunk. And it's the top chunk that's our focus in the House of Force. We can use our overflow to control what size malloc perceives the top chunk to be, because, as I mentioned earlier, many versions of GLIBC have no top chunk size integrity checks, and malloc will take this value as gospel. So let's check which version of GLIBC we're working with. When you issue the vmmap command, pwndbg lets you grep for any terms you specify afterwards. vmmap libc should narrow things down. From the output, we can see that this binary is linked against GLIBC version 2.28, which doesn't have any top chunk size integrity checks. For a list of which heap exploit mitigations were introduced in which versions of GLIBC, check the Mitigations section of the PDF. The eagle-eyed may have noticed this No Tcache extension. The Tcache is a malloc feature that was introduced in GLIBC version 2.26. We won't cover the Tcache in part 1 of the HeapLAB course, but be aware that some of our vulnerable binaries use malloc versions compiled without the Tcache. Rest assured that this is just to prove these techniques work on later versions of GLIBC, without having to learn about the Tcache first. If anything, the presence of the Tcache makes malloc easier to exploit. It's worth noting that regardless of which version of GLIBC a binary was built against, at runtime it will use whichever GLIBC version is available on the OS it's installed on. This means that just because a binary isn't vulnerable to exploitation on one platform, that it won't be vulnerable to exploitation when installed on a different platform. These coarse binaries are the exception to that rule, forcibly run against specific versions of GLIBC for learning purposes. Back to our vulnerable binary. Let's consider what we can do with our overflow. We control the top chunk size field, meaning we can convince malloc that this heap's top chunk is any size we want. This is a simplified Linux process memory map, much like the output of the vmmap command. Typically, the binary itself resides at the lowest address, followed by the default heap in a region known as the program break. Then there's often a large gap, followed by the libraries, including GLIBC, then another gap, and finally the stack at the highest address. If we overwrote this heap's top chunk size field with a large value, then from malloc's perspective, that top chunk could extend across this gap, overlapping sensitive data in the library or stack regions. But don't forget that our target data, those capital X's, resides in the data section of the binary at a lower address than the heap. But what if we wrote a really large value into the top chunk size field? Then it would appear as though it extended past the end of the virtual address space, wrapping around back to the start. Then we could make another large request from malloc, which would be serviced by this heap's top chunk, wrap around the VA space, and overlap the binary's data section. And that's exactly what we're going to do. We'll leverage this binary's overflow to overwrite the top chunk size field with a very large value. Then we'll make a large request from the top chunk that wraps around the VA space, spanning the gap between the heap and our target data, then make one final request that overlaps the target so that we can overwrite it. To achieve this, we're going to need to send some non-printing characters to the program, do some math, and make the whole process repeatable. This is where pwntools comes in. Close GDB and make a copy of the pwntools_template.py script. Call it what you want with the exception of pwn.py. The first thing pwntools scripts do is import a library named pwn.py, and your script will try to import itself. I'm calling my copy xpl.py, which is short for exploit and makes tab completion easy. Open the copy in an editor of your choice. I'll be using Vim just to show that we don't need anything special like an IDE to do this stuff. This is our first pwntools script. All it's going to do is start the house of force binary and send it any input that we tell it to. Don't be alarmed by the quantity of text here. Most of this is pwntools boilerplate and helper functions that I've added to avoid this becoming an exercise in Python. We're only going to write 4 lines of code to exploit this binary. Scroll to the bottom of the script. All we're concerned with is this region here between the dashed lines, which currently holds some example uses of those helper functions I mentioned. Lines starting with log.info are just printing debug information. Recall that this binary leaks the address of its heap. That's captured in a variable named heap. The elf variable represents the binary, and we have access to its symbols via elf.sim.symbolname. For example, elf.sim.target is the address of those capital X's we want to overwrite. The malloc function is a wrapper around option 1 from the binary's menu. It takes 2 arguments, the size to request and the data to send. This example does the equivalent of selecting option 1 from the program's menu, sending the value 24 when prompted for the size, then sending some arbitrary data, 24 capital Ys, when asked for data. This last line uses the delta function, which we'll cover shortly. When we run this script, pwntools will start the house of force binary, send it the input we've told it to, then return control to us via an interactive prompt. So let's try it. You can run the script from the command line or from within Vim using the bang./% command, where bang indicates what follows should be interpreted as a shell command, and % is replaced by the name of this buffer. pwntools starts by printing the checksec output for each binary it loads, in this case the House of Force binary and its GLIBC shared object. These 3 lines are the result of those log.info calls. And lastly, we're given an interactive prompt so we can talk to the program ourselves. Hit return to print the menu, and we can see that one of our 4 chunks has been allocated. But wouldn't it be great if we could inspect the heap at this point? We could attach GDB manually each time, but pwntools gives us a much simpler way to do so. Quit the program with option 3, hit return once to ignore the pwntools message about receiving an end of file, and again if you launched from Vim. This time, run the script with the GDB option, in all caps. pwntools will do exactly as it did before, start the binary, send its input, and give us an interactive prompt. But this time it will attach GDB to the process between the first and second steps, and open the debugging session in a separate terminal. Depending on your OS, you can use Alt or Option backtick to switch between GDB and the program prompt. If you're not using Ubuntu, that key combination might be different. I'm going to use this 2-windowed layout throughout the course, because it's the default setting on Ubuntu and doesn't require students to make a lot of changes to their environment to behave like mine. It is worth noting that you can get both pwntools and pwndbg to use different layouts that are much more efficient to work in than this, like tabs or split windows. Just check their respective documentation. We can break in GDB with Ctrl+C, then use viz to inspect the heap as usual. And it looks like our script worked. A 20 sized chunk has been allocated and filled with capital Ys. Notice that the heap addresses are different from what we've seen so far. This is because running your script with the GDB option attaches GDB to the already running process rather than starting it under GDB. This means that ASLR is in effect, and although we want our exploits to work under ASLR, debugging them with it active can be cumbersome. So next time we run our script, I'll show you how to temporarily disable it. Return to your editor by closing GDB, then hitting return. And let's declutter a bit by removing the log.info lines from our script. Now, we know that the next 8 bytes we send after these capital Ys will overwrite the top chunk size field. So let's append that value to the second argument of this malloc function. This is the part where we have to send non-printing characters. So to avoid typing a lot of \x's and accounting for endianness, we can instead use pwntools pack64 or p64 function, which is just a wrapper around struct.pack. We want to set the top chunk to a large value, so why not use the largest 64-bit value we can using 16Fs. Once you've added that to your script, run it again with the GDB option, and this time append the no ASLR option, again in all caps. Break in GDB and use the viz command, which shows us that we've successfully overwritten this heap's top chunk size field with a very large value. This is our House of Force primitive. malloc now considers this top chunk to be huge and will fulfill much larger requests from it than it otherwise would. So let's move on to the second phase of our attack. We're going to request enough memory from malloc to span the gap between this top chunk and our target data. Close GDB and head back to your editor. First, we'll need to calculate the distance between the top chunk and our target. We can use the delta function for this, which compensates for the fact that our allocation is wrapping around the VA space. Delta takes 2 arguments, a start and end address. The start address is the top chunk. We know its location because this binary leaks its heap address, which you'll recall our pwntools script captured in the heap variable. Add hex 20 to that value to account for the 20 sized chunk that we've already allocated, resulting in the address of the top chunk. The end address is the target, those capital X's in the binary's data section. Take hex 20 away from this value to stop just short of the actual target data. We could overlap the large chunk we'll be requesting with the target, but we'd have to write a lot of data into it before we reached the target, most likely causing a seg fault as the program attempted to write to read-only or unmapped memory. It's easier to stop just short, then request another small chunk that overlaps our target data. Now that we've calculated the chunk size we want, let's request it and write a single byte of garbage into it. Once you've added those lines, run your script with the GDB and no ASLR options. Break in GDB, and this time issue the dump quad target -16 command, which gives us a view of the memory surrounding the target data. There's the target, and this is the top chunk size field, sat right in the middle of the program's data section, which we can confirm using the top chunk command. Notice how we've scrubbed a lot of its size away. Moments ago, this was the largest possible 64-bit value. Now, the next request we make from malloc will be serviced from this rogue top chunk, and the first quad word of its user data will neatly overlap the target. And we can do this part manually. Continue in GDB, Alt or Option backtick to switch to the interactive prompt, use Option 1 to request a small chunk, and anything we write into it will overwrite the target data and subsequently be printed when we select Option 2. Great! Let's add that last request to our script. Quit the binary and return to your editor, where we'll add one more call to the malloc helper function. I'll request a minimum sized chunk and write the same string I used just now into it. This time, run your script without the GDB and no ASLR options to ensure that it works under production conditions. Select Option 2 to print the target, which confirms that we've successfully overwritten the target data with our own. And that's all there is to it. We've leveraged the House of Force technique to make an arbitrary write. To summarize, this binary has a heap overflow bug that we were able to leverage to overwrite that heap's top chunk size field with a large value. This was enough to convince malloc that the top chunk was much larger than it actually was, allowing us to make a large allocation from it that otherwise would have failed. The large chunk we requested spanned the gap between the heap and our target data. Then we made one last request for a chunk that overlapped our target, allowing us to overwrite it. If you're unsure of any of the steps we took, there's a solution script available for download from this section's resources. It does exactly what I've just showed you and is commented for clarity. Don't forget you can also find an overview of the House of Force technique along with all the malloc internals we've covered so far in the PDF. So we've learned the House of Force technique and leveraged it for an arbitrary write. In the next video, we're going to learn how to turn that arbitrary write into code execution. The question we're going to answer in this video is, how can we hijack the flow of execution with our arbitrary write? Well, let's think about this in terms of ASLR regions. We could target the stack, which might hold all manner of useful data like function pointers, not to mention saved return addresses. However, stack state is very program dependent. What's more, in this case, the stack is subject to ASLR, and we haven't been able to leak its address, so the stack is out. We could target the binary. Indeed, we already did this when we overwrote the target data. Tampering with structures like the PLT or FINI array can yield code execution. For the sake of completeness, the procedure linkage table, or PLT, is a writable array of function pointers. Every function the program calls that resides in an external library like GLIBC is represented in the PLT. The reason it remains writable for the program's lifetime is to support something called lazy linking, whereby a function's address is only resolved when it's first called. Overwriting PLT entries is a great way to hijack the flow of execution. For example, this binary uses the printf function provided by GLIBC. If we overwrite the printf PLT entry with the address of some code we want to execute, the next time the program tries to call printf, our code will be executed instead. The fini array is another array of function pointers. Each function in the fini array is called as the program exits. Overwriting fini array slots allows you to hijack the flow of execution if you can coerce the program into exiting. Unfortunately, you'll recall from the output of checksec that this binary was compiled with full relrow, meaning that both the PLT and fini array are marked read-only after initialization, so the binary is also out. We could target the heap. One advantage of doing so is that we wouldn't need a heap leak, because the distance between the top chunk and our target would be relative. It would be great if there were some function pointers or other sensitive data on the heap, but unfortunately, in this case, there's nothing aside from our own data, so the heap is out. Okay, well, we have a libc leak, so what can we target in libc? libc also has a procedure linkage table alongside two other structures called exit funcs and TLS detours, which behave similarly to the fini array. But although the GLIBC PLT is writable throughout the program lifetime, it can be difficult to trigger calls to the functions within it. What's more, both exit funcs and TLS detours are protected by something called pointer guard, which makes reliably tampering with them somewhat difficult. However, it turns out that there is a heap-specific way to hijack the flow of execution. I'm talking about the malloc hooks. Each of malloc's core functions, such as malloc and free, has an associated hook, which takes the form of a writable function pointer in GLIBC's data section. Under normal circumstances, these hooks can be used by developers to do things like implement their own memory allocators or to collect malloc statistics. We're going to use them to drop a shell. Make a copy of the exploit we wrote in the last video and open it in your editor. I'll just edit mine in place. Scroll to the 4 lines that we added. We'll leave the first line, that's what sets up our House of Force primitive, by overwriting the top chunk size field with a large value via the overflow. This time, the distance we want to cover with our large allocation is the difference between the top chunk and the malloc hook. We're going to use the malloc hook because it's the only one of malloc's core functions that we can reliably call in this binary. We don't need the delta function anymore because this chunk won't wrap around the VA space like it did before. So all we need to do is set the distance variable to libc, which represents the GLIBC shared object in our script, .sim to access its symbols, and the name of the malloc hook's symbol is __malloc_hook. Let's subtract hex20 from that address just like we did before, so the allocation stops just short of the malloc hook. And we want the difference between the malloc hook and the top chunk, which we'll calculate in the same way we did earlier, with the address of the heap plus hex20 to account for the 20-sized chunk we already requested. Let's see what sort of state this leaves the process in. Comment out the last request for now, then run your exploit script with the GDB and no ASLR options. Break in GDB with Ctrl+C, and this time we want to inspect the memory surrounding the malloc hook with dq ampersand for address of __malloc_hook -2. We use -2 instead of -16 because GDB does pointer math depending on the type we pass it. This null quad word is the malloc hook, and as I mentioned earlier, it's a function pointer. When it's null, like this, it's ignored, and calls to the malloc function work as normal. When it isn't null, however, calls to malloc are redirected to the address that it holds. The top chunk command reveals that our last request left the top chunk right here, preparing us to overwrite the malloc hook. Notice how this time we scrubbed a lot less from the top chunk size because the distance between the heap and our target was much smaller. So let's make another request from this top chunk and overwrite the malloc hook. Close GDB with quit or Ctrl-D and return to your editor. Uncomment the last request and replace the string we used to overwrite the target with the unmapped address 0x_deadbeef using the p64 function. Run your script with the GDB and no ASLR options, break, and inspect the malloc hook with the command print__malloc_hook. This confirms that it has indeed been overwritten by our deadbeef value. The next time the malloc function is called, execution will be redirected to this unmapped address. So let's continue, switch windows to the interactive prompt, and make a request for any size. Usually the binary would prompt us for data at this point, but it's not responding. Switch windows back to GDB, where we can see that execution has halted at the invalid address deadbeef. Great, this means that by overwriting the malloc hook, then calling malloc, we can hijack the flow of execution. The question now becomes, what do we want to execute? Often that's situation dependent. A denial of service may be all you need. Perhaps you want to leak sensitive information. In our case, we want a shell. And one way of achieving this is via GLIBC's system function. The man page for system shows that it's a simple function taking a single argument, a pointer to a string that's interpreted as a shell command. So if we redirect execution to GLIBC's system function and pass it the address of the string bin_sh, which is the path to one of the shell executables, this process will give us a shell. So let's head back to our editor and replace the invalid deadbeef address that we wrote into the malloc hook with the address of GLIBC's system function. Now all future calls to malloc will be redirected to system. Furthermore, any arguments originally passed to malloc will also be passed to system. This means that we can masquerade the address of our bin_sh string as the size of a request. The only remaining question now is, where can we write or find the string bin_sh? Well, in our case, we have a heap leak, so one way to achieve this could be to write the command onto the heap, perhaps when we make our large request, not forgetting to null terminate it. Then all we need to do is record the address of our command, which resides at the start of the second chunk's user data, so heap plus hex 30, and pass that address to malloc as if it were a request size. Now, when we run our script, this time under production conditions without the GDB and no ASLR options, that last call to malloc evaluates to system bin_sh, giving us a shell. So to summarize, we built our house of force primitive via an overflow by overwriting a heap's top chunk size field with a large value. Then we made a large request from that top chunk that spanned the gap between the heap and the malloc hook in GLIBC's data section. The next request we made yielded a chunk that overlapped the malloc hook, which we subsequently overwrote with the address of GLIBC's system function. Then we made one final request to malloc with the address of the command we wanted system to run, masquerading as the size argument. In this case, the command was bin_sh because we wanted a shell, and we'd written it onto the heap. The call to malloc became a call to system bin_sh, giving us the shell we wanted. There is an alternative to writing our command string onto the heap. The string bin_sh actually exists within the GLIBC shared object. The reason for this is that functions like system already do the equivalent of run bin_sh via the execve syscall, which is then used to run the command passed by the program. We can use the existing bin_sh string in the libc shared object like so. And when we run our script again, we get the same result, a shell. And that's it for the House of Force technique. It's quite a strong primitive and it works against GLIBC versions 2.28 and below. GLIBC 2.29 introduced a top chunk size check that compares the size of a top chunk against a variable called system mem, which mitigates this technique. The House of Force does require knowledge of the distance between a top chunk and your target, unless your target resides on the same heap, and that you're able to make arbitrarily large requests to malloc. Once again, if you're unsure of any of the steps we took, there's a commented solution script available for download from this section's resources. And don't forget, you can find an overview of the House of Force, along with all the malloc internals we've covered so far, in the PDF. In the next video, we'll learn the malloc internals required to understand our second heap exploitation technique, the Fastbin Dup.
Let's continue with our second technique, the Fastbin Dup, or duplication, beginning with some more malloc internals.
Something malloc does very efficiently is recycle unused heap memory. And this is achieved via the second of malloc's functions we're going to explore, free. Free is another simple function. You pass it a pointer to a chunk that you no longer need, and then you can forget about it, safe in the knowledge that it will be recycled if and when is necessary. From malloc's perspective, however, the unused chunk is linked into one of several free lists, which are, as they sound, lists of free chunks. Of particular interest to us are a collection of these free lists known as the Fastbins. Fast because the chunks in these lists are recycled fast, and bins because that's what the malloc maintainers call lists, at least when they're not calling them buckets. The Fastbins are just a small collection of singly linked, non-circular free lists that each hold free chunks of a specific size. And to help us visualize how the Fastbins operate, we're going to debug another small demo binary. Navigate to the Fastbin Dup directory and once again load the demo binary into GDB. Use the set context sections code command again to minimize noise, set a breakpoint on the main function, and run the program. The source panel shows us that the first thing this binary does is request 3 minimum sized chunks. We can pass the number of lines we want to execute as an argument to the next command. So next 3 will make those requests. Then the viz command shows us that the heap looks exactly as we'd expect it to, with 3 minimum sized chunks, A, B and C respectively. The source panel shows us that this program will now use the free function to recycle these chunks in the same order that they were requested. Before it does that, let's check the Fastbins with the Fastbins command. The output reveals that there are 7 Fastbins, each responsible for holding free chunks with sizes between hex 20 and 80. Although there are more Fastbins than this, these are the ones used under default conditions. The null to the right of each bin indicates that it's currently empty. Let's use the next command to free chunk A, followed by viz and Fastbins to see what's changed. We can see that chunk A has been linked into the 20 Fastbin. Recall that malloc addresses chunks by their metadata rather than their user data. The viz command has also annotated the same information here. But where is pwndbg getting this information from? There's no clear indication on the heap that anything has changed. This brings us to arenas. Arenas are structures in which malloc keeps all of its non-inline metadata, consisting primarily of the heads of each of those free lists I mentioned. A single arena can administrate multiple heaps, and a new arena is created along with an initial heap every time a thread uses malloc for the first time, up to a limit based on the number of available cores. The main thread gets a special arena called the main arena, which resides in the GLIBC data section, and it's the main arena that pwndbg is getting its current information from. Pwndbg does have some arena inspection commands, but we're just going to use dq to dump the first 20 quad words of the main arena, the symbol for which is main_arena. Compare what we're seeing here to the arena layout diagram in the PDF. This is the top chunk pointer. It keeps track of the address of an arena's top chunk. We were indirectly manipulating this in the House of Force technique. These are the heads of some of the other bins that we haven't covered yet, and this is the head of the 20 Fastbin, which currently holds the address of chunk A. Whenever a chunk that falls into Fastbin range is freed, its address is written to the head of the appropriate Fastbin in that heap's arena. If we freed a hex 30 sized chunk, its address would be written here, a 40 sized chunk here, etc. Now let's use the next command to free chunk B, followed by viz and fastbins. We can see that the 20 fastbin now holds two chunks, B and A, also annotated here. But arenas only have one fastbin slot per size, which, by reusing our dq command, we can see is now occupied by the address of chunk B. The remaining metadata of the 20 fastbin is stored in line, and we can see that the first quad word of chunk B's user data has been repurposed as a forward pointer, or FD, not to be confused with file descriptors. Chunk B's FD points to chunk A, and chunk A's FD is null, indicating the end of the list. Chunk user data can be repurposed like this because chunks are only supposed to be freed when no longer in use by the program. Freeing chunk C with next, followed by viz, fastbins, and our dq command, shows us that the process repeats whenever a chunk of the same size is freed. Chunk C is now the first chunk in the 20 fastbin, with its address written into the 20 fastbin slot in the main arena. The first quad word of chunk C's user data has been repurposed as an FD, which points to chunk B. Chunk B's FD points to chunk A, and chunk A's FD is null, indicating the end of the list. Note that the prev in use flags belonging to chunks B and C are still set, despite their previous chunks not being in use. The fastbins are the exception to the prev in use rule, and we'll see why that is in a later technique. For now, just understand that we won't expect to see any clear prev in use flags quite yet, despite dealing with free chunks. Here's a simplified visualization of what's just happened, with our three hex 20 sized chunks on the heap, and the main arena elsewhere in memory. When chunk A was freed, its FD became null, and its address was written into the 20 fastbin slot in the main arena. Then chunk B was freed, its FD adopted a pointer to chunk A, and chunk B's address was written into the 20 fastbin slot. Finally, when chunk C was freed, its FD adopted a pointer to chunk B, and chunk C's address was written into the 20 fastbin slot. Another way to visualize the fastbins is as a collection of stacks, the stack pointers for which are held in an arena. Every time a 20 sized chunk is freed, for example, it's added to the top of the 20 stack. The stack analogy is appropriate because fastbins are last in, first out, or LIFO structures, meaning that the next request for a 20 chunk will pop or allocate the chunk at the top of the 20 fastbin stack. We can confirm this behavior by issuing the next3 command, which executes 3 further requests for minimum sized chunks, labeling them D, E, and F respectively. We can use printd, print_e, and printf to confirm that malloc allocated the last chunk to be freed, chunk C, followed by chunk B, then chunk A, effectively popping them off the top of the 20 fastbin stack, rather than using more memory from the top chunk. And that's how the fastbins work. To summarize, they're a collection of singly linked, non-circular free lists that each hold free chunks of a specific size, from hex 20 through 80 under default conditions. They're last in, first out structures, meaning they operate just like a stack. The head of each fastbin list resides in an arena, but the remaining links between chunks in a fastbin are stored inline on the heap. When a request is made, if it's in fastbin size range, malloc will search the appropriate fastbin before attempting to allocate from the top chunk. If you want to refresh your knowledge on the fastbins, take a look at the Fastbins title under the Arenas section of the PDF. You can also check out the malloc flowchart section if you want to better understand the order in which bins are searched during allocation. Now that we've got an understanding of the fastbins, we can move on to our second vulnerable binary and start learning about the Fastbin Dup technique.
In this video, we'll take on another vulnerable binary to learn our second heap exploitation technique, the Fastbin Dup.
I like to give credit where credit's due, but its origins are unclear. It's a more recent technique than the House of Force, and I've seen it documented as a Fastbin attack as early as 2014. But it's probably been around for longer. Either way, let's explore the vulnerable binary for this technique. From the Fastbin Dup directory, load the Fastbin Dup binary into GDB. It's another CTF-style binary written in C, this time with a different class of heap bug. We can run checksec from within GDB, which shows us that full relrow, stack canaries, and NX are all enabled. The binary isn't position independent and is linked against GLIBC version 2.30 compiled without the tcache. Run the program without setting any breakpoints. A libc address is leaked, but no heap address this time. We're being prompted for a username. For now, I'll just enter some garbage data. Now we're presented with a familiar numbered menu. Option 1 allows us to request up to 7 chunks. Just like before, we're prompted for a request size, but we're limited to fastbin sizes only, hex 20 through 80. An 80 sized chunk holds 120 bytes of user data, so that's the largest request we can make. I'm requesting a 30 sized chunk. One way to request a chunk of specific size is to take the desired chunk size, in this case hex 30, and subtract 8 for hex 28, which is the amount of user data a chunk of that size holds. Then we're asked for any data we want to write into that chunk. I'll send some more garbage data. Let's break in GDB and inspect the heap with viz to check everything is as expected. There's our 30 sized chunk with whatever garbage data we decided to write into its user data, followed by the top chunk. Continue and hit return to print the menu again. Option 2 allows us to free chunks by index, starting at 0. So let's free our 30 chunk at index 0. Break and inspect both the heap and fastbins. The 30 sized chunk has been linked into the 30 fastbin, and the first quad word of its user data has been repurposed as a forward pointer, which is null because it's the first chunk to be linked into this bin. If we continue and hit return, we can see that option 3 prints the target. Once again, our first objective is to overwrite the target data, proving that we can leverage the Fastbin Dup technique for an arbitrary write. This time the target is part of a struct named user, which also holds the username we gave earlier. Let's confirm this by breaking again and printing the user struct. If we want more information on a struct, we can use GDB's ptype command to inspect it, which shows us that the user struct holds 16 bytes of our username, followed by the target. If you want to visualize this layout in memory, use DQ, not forgetting the ampersand. Here's our username, and here's the target data. In a moment, I want you to pause this video, familiarize yourself with the Fastbin Dup binary, and see if you can find the bug. Once again, there's no need to go digging through assembly, just have a play with the program's menu and see if you can get it to crash or exhibit any strange behavior. Go ahead and pause now. If you found the bug, great work. If not, I can tell you that this binary has a so-called double free bug. A double free is when a program can free a chunk that's already free, which sounds benign. But let's think about what effect that might have. If we freed our 3.0 chunk twice, it would get linked into the 3.0 fastbin twice, meaning that it could be allocated for two different things simultaneously. For example, it might be allocated to hold some sensitive data, like an admin password hash, then allocated again from the same fastbin to hold some user-controlled data, which could lead to the user being able to read or overwrite that sensitive data. So let's try to double free our 3.0 chunk. Get your program back to the same state as mine by running it under GDB, setting any username, requesting a 3.0 sized chunk, and freeing it. I'll return to the program with continue. Then we'll both select the free option. Our 3.0 chunk is at index 0, and we've already freed it once, so let's free it a second time. Something's wrong. GDB has stopped, and if we scroll up to the last output from the program, we see that it received the abort signal. Processes don't often abort, and if they do, it's a sure sign we've triggered one of GLIBC's heap exploit mitigations. To find out more about which mitigation we've triggered, use the frame command, which can be shortened to just F, to switch to frame 4 within the int free function. Int free is just the name for part of the free procedure that does most of the heavy lifting. Issue the context code command to print the source lines surrounding the last call made from int free. Here's the mitigation, and it's explained by this comment. Check that the top of the bin is not the record we are going to add, i.e. a double free. This is one of many GLIBC heap exploit mitigations. Most Linux memory allocators have few, if any, mitigations like this, but GLIBC has been around for a long time and has a well-protected heap implementation. This particular mitigation is here to stop the same chunk ending up in the fastbins twice in a double free scenario, and if it's triggered, this error message is printed and the process receives the abort signal. But we're exploit developers. When we come across a mitigation, we first consider how to bypass it. So what is the fastbins double free mitigation checking for? The comment says that when the top of the bin, meaning the value in that fastbins slot in the arena, is the same as the record being added, meaning the chunk being freed, then that's a double free and the process should abort. The viz and fastbins commands show us that our 3.0 chunk was indeed at the top of the 3.0 fastbin when we tried to free it for the second time. But what if a different chunk was at the top or head of the 3.0 fastbin when we tried to double free? There doesn't seem to be any accounting for that scenario in the mitigation code. So let's try it. Close GDB, make a copy of the pwntools template Python script, and open it in your editor. Scroll to the bottom, and once again, we're only interested in what's between the dashed lines. The first thing this script does is deal with the username prompt, setting a username of George, which we can change later. It then uses the malloc helper function, which works the same way as in the House of Force scripts, to request two 3.0 sized chunks and fill them with garbage data. The malloc helper function returns the index of the chunk it requested. This way, we can use variables like chunk A and chunk B to keep track of chunks without having to remember their index. This time, we've also got a free helper function, which takes a single argument, the index of the chunk you want to free. Like the malloc helper function, it's just a wrapper around the free option of the binary, and the script uses it here to free both chunks A and B. Let's run this script with the GDB and no ASLR options, break with Ctrl+C, and inspect the heap with viz and fastbins. We see chunks A and B filled with capital A's and B's respectively, and note that both have been freed into the 3.0 fastbin. Importantly, chunk B is at the top of this bin since it was the last chunk to be freed. Chunk B has a forward pointer that points to chunk A, and chunk A's FD is null. So what happens if we free chunk A now? It's already linked into the 30 fast bin, so it would be a double free. But it's not at the top of the bin, that's chunk B. Well, let's try it. Continue in GDB, switch to the program window, hit return, and free chunk A at index 0 for the second time. The first thing you'll notice is that the program doesn't abort like before. Switch back to GDB, break, and inspect the heap again with viz and fastbins. Chunk A is now at the top of the 30 fast bin and has a forward pointer that points to chunk B, but chunk B's forward pointer still points back to chunk A. We've turned a non-circular list into a circular one. And we can see chunk A is annotated as being linked into the 30 fast bin twice. We've successfully bypassed GLIBC's Fastbins double free mitigation and linked a chunk into the same bin twice, also known as a Fastbin Dup. Now, unfortunately, the example I gave earlier of requesting the duplicated chunk for two different purposes doesn't apply here. There are no admin password hashes on this heap, and besides, we want an arbitrary write. So consider this. What if, having performed our Fastbin Dup, we request another 30-sized chunk? We know the fastbins take precedence over the top chunk, so we'd be allocated chunk A. Then we'd be in a position of controlling chunk A's user data, because it was legitimately allocated to us, whilst the first quad word of that user data was still being used as a forward pointer in the 30 fast bin. That could allow us to tamper with said FD, linking a fake chunk that overlaps our target into that fast bin. Then we could request that fake chunk and overwrite our target data. Let's give that a go, taking it step by step. Close GDB and return to your editor. We can remove the example title. Then the first thing we want to do is use the free helper function to double free chunk A, just like we did manually a moment ago. That sets up our Fastbin Dup. Next, we want to request another 30-sized chunk. Label it what you want. I'll label mine Dup. malloc will service this request with chunk A because it's at the top of the 30 fast bin. Whatever we write into the first quad word of this Dup chunk will be treated as a Fastbin forward pointer, because chunk A is now both allocated to us and free simultaneously. If we write the address of the user struct here, we're effectively linking a fake chunk that overlaps our target data into the 30 fast bin. Let's run our script with the usual options, break in GDB, and see what state we've left the heap in with viz and fastbins. Chunk B is now the first chunk in the 30 fast bin, followed by chunk A. But chunk A's FD points to the user struct now. And if we start requesting 30-sized chunks, we'll get chunk B, then chunk A, then the third chunk we request will overlap our target data. So let's add those requests to our script. Close GDB and return again to your editor. Add 2 more requests for 30-sized chunks. Then add a third. This one will overlap the target data. Overwrite the target with whatever you like. Then run the script with the usual options. We've hit a snag. GDB has immediately stopped, and from the backtrace panel, we can see that the abort function was again called. Use the frame command to switch to frame 4 within the int malloc function. Much like int free, the int malloc function actually does most of the memory allocation heavy lifting. Issue the context code command to print the source lines surrounding the last call made from int malloc, and there's our error message, which is much more cryptic this time. It simply reads memory corruption brackets fast. This one isn't commented, but it's checking whether the size field of the chunk malloc is about to allocate is the same as the size of fastbin it's being allocated from. After all, it wouldn't make sense for a 90 sized chunk to find its way into, say, the 30 fastbin, because the 30 fastbin only holds 30 sized chunks. If we use dq to inspect the user struct, we see that our fake chunk's size field is 0, which is why it's failing the size field check. But ptype reminds us that we control this memory via our username. So what if we set up a fake size field? Let's give it a go. Return to your editor and change the username to 8 bytes of garbage, I'll use a null quad word, plus a fake hex 31 size field using the p64 function. Run your exploit script with the usual options, and this time all seems well. Switch to the program window, pick the target option from the menu, and if everything went to plan, you'll see your data printed instead of the target data. Switch back to GDB, break, and use dq to inspect the memory around the target. You'll see your fake size field that we set up to fool the fastbin size field check. Awesome! We've leveraged the Fastbin Dup technique to make an arbitrary write. To summarize, this binary has a double free bug that we used to link a chunk into the same fastbin twice. We were able to bypass the fastbin's double free mitigation by ensuring that our victim chunk wasn't at the top of its fastbin when we freed it for the second time. Then we requested that duplicated chunk and wrote a pointer to a fake chunk overlapping our target memory into the first quad word of its user data. Because the duplicated chunk was still linked into the fastbin when we did this, the first quad word of its user data was being used as a forward pointer. This had the effect of linking our fake chunk into that fastbin. We then requested our fake chunk from the fastbin and used it to overwrite the target data. We were able to bypass the fastbin's size field check by using data we controlled near the target to set up a fake size field. As usual, there's a commented solution script available for download from this section's resources. There's an overview of the Fastbin Dup technique, along with all the malloc internals we've covered so far, in the PDF. There's also a mitigations section that has information on all the GLIBC heap exploit mitigations to date. In the next video, just like we did for the House of Force, we'll turn this arbitrary write into code execution. In this video, we're going to drop a shell from our second vulnerable binary using the Fastbin Dup technique. Once again, we'll be targeting one of the malloc hooks, which you'll recall can be used to intercept calls to the core malloc functions. This time, we're able to call free, so why not hijack the free hook instead of the malloc hook? One advantage of using the free hook is that its first and only argument will always be a pointer to chunk user data, meaning that if we overwrite the free hook with the address of GLIBC's system function, then freeing a chunk that contains our command string becomes the equivalent of passing that command to system. Make a copy of the exploit we wrote in the last video and open it in your editor. I'll edit mine in place again. Scroll to the lines we added. We're going to start by changing the address of the fake chunk we linked into the 30 fastbin. Instead of overlapping our fake chunk with those capital X's in the binary's data section, we want to overlap it with the free hook. So let's change the line where we link our fake chunk into the 30 fastbin. Replace the address of the user struct with the address of the free hook, the symbol for which is __free_hook, and subtract 16 bytes, remembering that malloc treats chunks as starting 16 bytes before their user data. This way, the first quad word of our fake chunk's user data neatly overlaps the free hook. Next, we want to change the line where we request our fake chunk and write to its user data. This is what's going to get written into the free hook, so instead of our string, we want to use p64 to write the address of the system function. Now we're set up to populate the free hook with the address of system. Let's run our script with the GDB and no ASLR options. Something's gone wrong, and we can see a call to abort in the backtrace. Switch to the int malloc frame and use context code to see the last call made from it. This looks familiar. It seems as though our fake chunk has failed the Fastbins size check, and on using the dq command to inspect the memory surrounding the free hook, it's clear why. The free hook is here, and our fake chunk size field is here, a null quad word that this time we don't control. Even worse, it looks like there are no naturally occurring viable fake size fields anywhere nearby. The furthest we could have used is here if an 80 value were present. So it looks like the free hook isn't a viable option after all. But what about the malloc hook? Let's inspect the surrounding memory just like we did with the free hook. The malloc hook is here, and this time there are some addresses nearby, but nothing that would make a convincing size field. All these values are far too large. But let's double check using pwndbg's findFakeFast command, which can help locate viable fake chunks that qualify for the Fastbins. Pass it an address, and it prints the locations of any fake chunks that overlap that address. Its output is verbose, but it seems to have found a candidate fake chunk at this address, 35 bytes before the malloc hook. So let's see why pwndbg considers this a candidate by dumping memory at that address. It appears as though pwndbg has coerced a 7f size field by misaligning one of the addresses in memory before the malloc hook. The size field is comprised of the 3 most significant bytes of this quad word and the 5 least significant bytes of the following quad word. If that seems backwards, remember that GDB is displaying these little endian values to us in reverse order. Using db, short for dump bytes, to display the memory can help to clarify things, as it shows how the 7f and following null bytes are contiguous. And, believe it or not, we can use this size field. When allocating from the Fastbins, malloc does not check for alignment, nor does it check that a chunk's flags are valid. Some flag combinations can cause a crash, but 0f will work just fine. But surely the address we're taking this 7f byte from will be subject to ASLR under production conditions. And it is. But on most x86 Linux platforms, libraries are always mapped at addresses starting with hex 00007f. If you're using a Mac right now, you can confirm this by typing vmmap $$ into a terminal. And the address that we're taking the 7f byte from is part of the standard I/O feature, which we'll cover in a different technique. Suffice to say that it will always be present. Furthermore, the following quad word that we're taking the zeros from is a padding quad word, which will consistently be null. So even under production conditions, we will always be able to coerce this 7f size field. Armed with this knowledge, let's head back to our editor and modify the exploit. First, we'll need to align our fake chunk with that 7f size field by replacing the free hook with the malloc hook and subtracting 35 bytes from it. That was the distance between the hook and the start of the fake chunk. Then we have to change all our request sizes so that we're dealing with 7.0 sized chunks instead of 3.0. This way we link our fake chunk into the 7.0 Fastbin, and the 7f size field will pass the size check. Lastly, we need to add some garbage to the start of the data we write into our fake chunk, because the first quad word of its user data is no longer neatly aligned with the malloc hook. So add 19 bytes of garbage to the start of the second argument of this call to the malloc helper function. Once you've made those changes, run your script with the usual options. This time, GDB doesn't stop, and if we break and dereference the malloc hook, printing a handful of instructions at the destination with the U command, we see that the malloc hook points to the system function. Now, all that's left to do is call malloc with the address of a command string as the first argument, just like we did in the House of Force binary. However, recall that this program limits our request size to a maximum of 120 bytes. That's not nearly high enough to be a mapped address. But what if we didn't need to pass any arguments? What if there was a way we could drop a shell simply by redirecting the flow of execution once? Enter OneGadgets. From the system man page, we can see that all system does is use execl, which is a wrapper around execve, to run bin sh with the C option followed by the command passed as an argument. This means that there must exist in the GLIBC shared object some code that does the equivalent of execve bin sh, i.e. drop a shell. And these code snippets are known as OneGadgets. Instead of searching for these gadgets manually, we can use David942j's OneGadget Finder that we installed at the beginning of the course. The syntax is OneGadget followed by the path to the libc binary your program is using. Normally, this would be a constant path for all binaries on the system, but because our vulnerable binaries aren't linked to the system's glibc version, we need to use this one-liner, which you can find in Appendix A of the PDF. OneGadget prints the offset from the beginning of the libc shared object for each gadget it finds, followed by the constraints of that gadget. For example, the second gadget starts at hex E1FA1 bytes after the start of the libc shared object, and its constraint is that when execution is redirected to this gadget, the value at stack pointer plus hex 50 must be null. That's because for this particular gadget, the argv array of the execve call starts at stack pointer plus hex 50. On most systems, bin sh is a symlink to dash. In fact, if we type man sh, it's the dash man page that opens. Dash is very sensitive to malformed arguments, including unreadable addresses, non-existent options, and non-existent paths. And it will fail if it comes across any one of these. That's why ensuring the first entry in its argv array is null is the safest way to guarantee it doesn't attempt to process any potentially broken arguments. So let's find out if we're able to meet the constraints of any of these OneGadgets. We'll need R12 and 13 to be or point to null, or stack pointer plus hex 50 to be null, or meet these RSI and RAX requirements. Run your script with the GDB and no ASLR options. Break and set a breakpoint on the address in the malloc hook by dereferencing it with an asterisk. Continue and switch to the program window where we'll trigger malloc by requesting a chunk of any size between 0 and 120. Switch back to GDB, which has hit our breakpoint. This is the state of the registers and stack that will be passed to our OneGadget. Let's inspect the registers with context reg. It looks like R12 and 13 aren't viable. Neither are RSI and RAX. That just leaves stack pointer plus hex 50. Dump the stack with the stack command, followed by the number of quad words you want to dump. The offset from the stack pointer is shown on the left, and unfortunately, stack pointer plus hex 50 isn't null. But it is a valid address, and the C11 standard states that the first entry in any argv array typically represents the name of the program being invoked, which in most cases is ignored. The next entry is null, and that's good enough to satisfy the constraints of this OneGadget, even if the OneGadget finder doesn't think so. We'll return to our editor and prepare to use this OneGadget by substituting the address of the system function with the address of our OneGadget. The offset was hex E1FA1 bytes from the libc load address. An alternative to remembering the offset is to use the OneGadget script option, which runs your exploit script with every gadget it finds. We'll add one last call to the malloc helper function to our script. The request size must be between 0 and 120 to be accepted by the program and trigger malloc, but the data doesn't matter. After all, just calling malloc at this point should be enough to drop a shell. The argument is irrelevant and the program won't even get as far as asking us for data. Once you've made those final changes, go ahead and run your exploit under production conditions. And you should get a shell. And that's one method of obtaining arbitrary code execution via a Fastbin Dup. In summary, we built our Fastbin Dup primitive via a double free bug, which we used to link a fake chunk overlapping the malloc hook into the 7.0 Fastbin. We were able to allocate this fake chunk by using existing consistent GLIBC metadata as a size field. It didn't matter that the flags weren't valid or that the fake chunk was misaligned, because malloc doesn't check for those inconsistencies when allocating from the Fastbins. Then we wrote the address of a OneGadget over the malloc hook, a OneGadget being an existing set of instructions which, when executed, drops a shell. Finally, we triggered a call to malloc, which was redirected via the malloc hook to our OneGadget, giving us our shell. The Fastbin Dup can be a powerful primitive and works on GLIBC versions 2.31 and below. It does require knowledge of the address of your target and requires an attacker to forge or use an existing size field to pass the Fastbin's size field check. As usual, there's a commented solution script available from this section's resources and an overview of the Fastbin Dup technique along with all the malloc internals we've covered so far, plus OneGadget tool use in the PDF. In the next video, we'll put to the test what you've learned so far when we take on the first challenge binary. Welcome to your first challenge binary. In this video, I'll begin by explaining how challenges work. Then, I'll introduce the challenge binary and let you get on with solving it. Start by navigating to the challenge-fastbin dup directory. This challenge will test what you've learned so far about fastbins and arenas. The second challenge will involve writing a full exploit including leaks, but we're starting easier with this one. All you have to do is drop a shell from the Fastbin Dup 2 binary. I'll walk with you through the initial investigation of the binary, then you'll pause the video to take on the challenge yourself. If you get stuck or just want to verify your progress, you can unpause the video and I'll take you through the next phase of the exploit. So let's start with the usual drill of learning which protections this binary employs using checksec. Like everything so far, it's compiled with full relrow, meaning that we'll have to rely on the malloc hooks to get code execution rather than on the binary. It has stack canaries and NX, and this time it's also position independent, meaning that we don't know the location of the binary in memory. Note that position independent programs use different base addresses for the binary and heap, even when running without ASLR enabled, so expect to see different values than you're used to when using heap commands. Lastly, the binary is linked against GLIBC version 2.30 without tcache support. Run the binary under GDB and we'll see what we're dealing with. We still have a libc leak, which will of course come in handy. We can request a few more chunks, this time up to 13, and we can still only request fastbin sized chunks. But it looks like there's a catch. We're unable to request 70-sized chunks. That means any request size that would result in a 70-sized chunk being allocated won't be processed. For example, I can request hex 58 bytes of user data, resulting in a 60-sized chunk being allocated, which I can confirm by breaking in GDB and inspecting the heap. But my request for hex 59 bytes is denied, because it would result in a 70-sized chunk being allocated. This is the main obstacle you'll need to deal with. Remember that requesting 70-sized chunks was critical to our success with the last Fastbin Dup binary, because it allowed us to use that existing 7f size field for our fake chunk overlapping the malloc hook. This isn't about coercing the program into letting you allocate 70 chunks. It's about finding an alternative way to overwrite one of the malloc hooks via the Fastbin Dup technique. The rest of the program works just like the Fastbin Dup binary. The free option lets us free chunks by index, and the double free bug is still present. There's no target option this time because our only objective is to drop a shell. There's a pwntools template script to get you started. Don't forget that the libc symbols are accessible via libc.sim.simplename. For example, libc.sim.main_arena for the main arena. And if you need to refresh your memory on any pwndbg commands, pwntools functions, or the OneGadget tool, take a look at Appendix A of the PDF. I would strongly recommend revisiting the arena layout diagram of the PDF, especially with regard to the proximity between the fastbins and the top chunk pointer. Alright, now's the time to start planning your exploit. We know that we can leverage this program's double free bug for a Fastbin Dup. The question is, how are we going to leverage that Fastbin Dup to overwrite one of malloc's hooks if we can't request 70-sized chunks? In a moment, pause the video and see how far you can get on your own. If you need a steer, unpause and I'll do my best to help you out. Don't worry if you can't do everything on your own, these challenges are designed to be difficult. Best of luck. Okay, I've added some lines to my copy of the template script. Notice that whenever I'm able to write to a chunk, I use a different letter to mark that chunk in memory. That makes identifying specific chunks in a memory dump a bit easier. I've used the free option to double free chunk A into the 50 fastbin. There's nothing special about that bin, it's just the size the template was already using. Then I've requested the same size back and overwritten its fastbin FD. Normally we'd put the address of a fake chunk here, but right now we don't have a viable size field to anchor, as it were, our fake chunk. I've also requested chunks B and A from the 50 fastbin so that my fake chunk, or in this case just a garbage value, ends up at the head of the 50 fastbin. Usually what we'd do at this point is allocate the fake chunk. But let's consider what coming this far has achieved. I'll run my script with the GDB and no ASLR options. The fastbins command shows that my garbage value is at the head of the 50 fastbin. Inspecting the main arena directly with the DQ command shows just that, my deadbeef value in the 50 fastbin slot. So, by its nature, the Fastbin Dup allows us to manipulate memory in an arena. Consider how that might be useful when looking to create viable size fields for a fake chunk. You can download a copy of my script so far from this section's resources. It's labelled as template number 2. Pause the video again and see if you can make a little more progress. If you got this far without help, then you're doing extremely well. And if you didn't, don't worry, these challenges aren't easy, and it's normal for them to take hours, if not days, to solve, especially if you're new to exploit development. They're here to encourage you to do things like browse the malloc source, read the man pages for things like the system function and the dash shell, and, most importantly, think like a hacker. Alright, I've added some more lines to my script, which again you can download a copy of from this section's resources. It's labelled as template number 3. The first part is the same as before, but I've swapped the garbage deadbeef value for a fake size field, hex 61, which will get written into the main arena in its place. If you hadn't already guessed, I'm going to use that size field to link a fake chunk into the main arena itself. That's what the second part of this script is doing. I've performed another Fastbin dupe, this time against the 6.0 Fastbin. I've used that to link a fake chunk into it that overlaps the main arena. Main arena plus hex 20 will line up my 6.1 size field I wrote there in the previous dupe with the fake chunk's size field. I've also made 2 more requests for 6.0 sized chunks so that my fake chunk will be next to get allocated from the 6.0 Fastbin. I'll run my script under GDB to show you what I mean. The Fastbins command shows us that my hex 61 value is now at the head of the 50 Fastbin, and a main arena address occupies the head of the 60 Fastbin. Both of these are the result of 2 different Fastbin dupes. Inspecting the main arena directly shows where both of those values reside. This is the 50 Fastbin slot, and this is the 60 slot. The next chunk to be allocated from the 60 Fastbin starts here, and we'll use my 6.1 value as a size field. Hex 6.1 is a legitimate size value for a chunk in the 60 Fastbin, so the Fastbin size check will pass. I'll demonstrate this by manually requesting a 6.0 sized chunk and writing some data into it. When I return to GDB and dump the main arena, we see that my data, those hex 59 bytes representing my capital Ys, have been written there. So we can use one Fastbin dupe to set up a fake size field in the main arena, then a second dupe to allocate a chunk there, giving us the ability to overwrite malloc metadata stored in an arena, for example, the top chunk pointer. Pause the video once again and see what else you can come up with. Return here if you need some more advice. I've added just one more line to my script. It requests the fake chunk overlapping the main arena and writes some data into it, just like I did manually before. You can also grab a copy of my script so far from the resources section labelled as template number 4. This time I've written garbage data up until the top chunk pointer, which I've then overwritten with the address of the malloc hook -16. We briefly touched upon the top chunk pointer when we were introduced to arenas, and it's what we were indirectly manipulating during the House of Force technique. I've chosen the malloc hook because our top chunk is going to need a size field that isn't 0, and as we've seen, there aren't any existing viable size fields near the free hook. I'll run my script and dump the main arena to show you what state it's in. We can see the fake 6.0 chunk, some of its user data has been filled with garbage, and the top chunk pointer has been overwritten. If we use DQ to view memory near the malloc hook, we see that malloc now considers the top chunk to start here, meaning this address, which incidentally is another one of malloc's hooks, has become the new top chunk size field. Now we're in an almost identical situation to the final stage of the House of Force. All that's left to do is make a request that will be serviced from the top chunk, so we can overwrite the malloc hook. Any size that has an empty fastbin will do, so I'll request a 20 sized chunk manually. But this time, it's not that simple. GLIBC has detected that there's something wrong with the top chunk size field. Now, the House of Force binary was using GLIBC version 2.28. This binary, you'll recall from the checksec output, is using GLIBC version 2.30. The mitigations section of the PDF reveals that GLIBC version 2.29 introduced a top chunk size field integrity check. If I return to GDB, switch to the int malloc frame, and issue the context code command, we can see that check. Malloc is comparing the size of the top chunk to something called AV system mem. AV is a variable that represents the arena administrating this heap, in this case the main arena, and system mem is the current amount of memory that arena has checked out from the kernel, a value which should be familiar, hex 21000, the initial size of our heap. If malloc notices that a top chunk is larger than the total memory its arena has checked out, then there's clearly something wrong and it will abort. Currently, we're using a GLIBC address as our counterfeit top chunk size, which is much larger than the system mem value. Pause the video again and consider how we might overcome this issue, remembering that just like other chunks, the top chunk doesn't necessarily need to be 16-byte aligned. Unpause the video if you need a hand figuring this part out. We were dealing with the top chunk size integrity check, which was comparing our fake top chunk size, a GLIBC address, to the main arena's system mem value, and finding that it was much too large. One way we can pass this check is to use the same misalignment trick we used against the first Fastbin Dup binary. Everything I've showed you so far is available for download from this section's resources, labelled as template number 5. I've amended the line on which we overwrite the top chunk pointer in the main arena. I've changed malloc hook -16 to malloc hook -35, the same value that we used in the last exploit to leave us with a reliable size field of hex 7F. We could also get away with using 36, even though the least significant byte would be subject to ASLR, the total would still always be less than system mem. I'll run my script and dump memory near the top chunk. Now our top chunk has a size field which is much less than system mem. We can safely request a chunk from it and overwrite the malloc hook. Don't forget to account for the garbage you'll need to write to make up the distance between the new top chunk location and the malloc hook. Last time we had to use 19 bytes. We'll need to employ a one gadget to drop our shell since, just like the first Fastbin Dup binary, our request sizes are too limited to pass in addresses. Appendix A of the PDF has an example of the one gadget tool use if you need a reminder. There is one last wrinkle to this challenge. It's okay if you don't get it on your own because it's something that we've only dealt with peripherally. But take some time to think about it. You'll find that you're unable to meet the constraints of any of the one gadgets in this version of GLIBC. But we've learned that the constraints printed by the tool aren't always as strict as they seem. Take a look at the man page for the dash shell, specifically the arguments that can be passed on the command line and therefore end up in the argv array. Pause the video now and have a crack at this last phase. Take your time, and if you find yourself really stuck, then unpause the video and we'll wrap this challenge up. Alright, let's get this one gadget working. I've chosen the same gadget that we used against the last Fastbin Dup binary, with the constraint that stack pointer plus hex 50 is null. If you need to catch up to this point, you can download my script from this section resources, labelled template number 6. I've added a line to my script that overwrites the malloc hook with the address of the one gadget I selected. For now, that line is commented out in favour of one that overwrites the malloc hook with a garbage value instead. This is a quick and dirty way of ensuring GDB stops at the exact point we want it to, so we can inspect the program context. Below that line is a further call to the malloc helper function to trigger a call through the malloc hook. When I run my script with the usual debugging options, the program segfaults at the garbage address I supplied. Now we can use stack 14 to see if our gadget's constraints will be met. Stack pointer plus hex 50 isn't null, but we know it's still safe since it's only argv0 and the address is readable. Unfortunately, argv1 isn't null either, which was how we got away with using this gadget last time. But it does point to memory that we control. Notice how the next 3 argv arrays are the same values I've been using to mark chunks, with these capital L's corresponding to argv1. This situation is of course program dependent. You might not be so lucky with different binaries. In this case, we're fortunate, because it means we can manipulate the first argument passed to the dash shell and potentially avoid it failing. If you've been experimenting with dash, you'll have noticed that it's sensitive to malformed arguments. Passing a non-existent option or file name to it will not result in a shell. What's worse is that even if the first argument is valid, it will continue to parse arguments until it hits a null, failing on any that are malformed or unreadable. If you've been browsing the dash man page, however, you may have discovered a couple of solutions to this problem. The first is that if dash comes across a valid file name, it will attempt to parse it for further commands, ignoring any succeeding arguments. So if you're able to write your commands to disk, then this is a viable option. A second, perhaps more practical solution is to pass the -s argument, which starts reading commands from standard in, ignoring any succeeding arguments. So I'll return to my editor and swap in the line that writes the address of our one gadget into the malloc hook. Running the script now prints the error m can't open L. Those strings come from the data I used to mark chunks in my script. So if I replace the L marker with the -s option, not forgetting to null terminate the string, then run the script under production conditions without the GDB and no ASLR options, I finally get a shell, and hopefully so do you. To summarize, our binary had a double free bug and a libc leak, but wouldn't allow us to request 7.0 sized chunks. So we leveraged the double free to make 2 Fastbin Dup attacks. We used the first to write a fake size field into the main arena, then the second to allocate into the main arena, overwriting the top chunk pointer. We aligned the top chunk pointer with a reliable libc address so that our fake top chunk had a size field that passed the top chunk size integrity check. Then we made a request from that top chunk, overwriting the malloc hook with the address of a one gadget. The one gadget constraints couldn't be met, but because we controlled the first argument passed to the dash shell that is invoked, we were able to pass the standard in option, avoiding dash parsing any malformed arguments and finally giving us our shell. A working exploit for this challenge, complete with comments, is available from this section's resources. Don't forget to review the PDF if you need to refresh your memory on arena layouts, the Fastbins, the Fastbin Dup technique, or any of the pwndbg commands and pwntools functions we've covered so far. There is one big advantage to controlling 2 or more arguments passed to a one gadget. Say we're attacking a set UID binary. I'll turn the challenge binary into one now. If I run my exploit, the shell I get still belongs to the user I ran the script as. That's because most modern shells will reset your effective UID if it doesn't match your actual UID. This is a safety feature to protect against exactly this sort of situation. When using the system function, there isn't much we can do about this, since by the time we've invoked a shell, the initial call to execve bin sh will already have reset our effective UID. But when using a one gadget, we're passing arguments straight to that initial invocation of dash. This means we can pass the -p option, which disables this behavior. I'll add the priv option to my script at what will become argv1, keeping the standard in option, which we still need, at what will become argv2. Now when I run the script, I get a shell, but this time it doesn't reset my effective UID. That last part isn't necessary to solve the challenge, but it's a nice trick you can do with one gadgets. I hope you enjoyed your first challenge binary. If you solved it without help, then that's extremely impressive. If not, that's totally expected. As I said earlier, they're designed to be very difficult. Either way, I hope you learned something. In the next video, we'll get back to learning malloc internals again, so we can understand our next heap exploitation technique, the unsafe unlink.
Let's continue with our third technique, the unsafe unlink. And we'll need to start with some more malloc internals.
So far, we've only seen what happens to chunks small enough to qualify for the Fastbins when freed, hex 80 and below. We'll be introducing another bin, called the Unsortedbin, and the concept of chunk consolidation. Navigate to the unsafe unlink directory and load the demo binary into GDB. Set the context output to just source code, set a breakpoint on the main function, and run the program. We know what requesting chunks from malloc looks like by now, so use next2 to make those first 2 requests, followed by viz, which shows us that we've got 2 hex 90 sized chunks, A and B, on the default heap. Before, when we freed chunks into the Fastbins, they didn't have any noticeable effect on their surrounding chunks. Neither did being next to the top chunk change their behavior when freed. But watch what happens when we free chunk B, which is both too large to qualify for the Fastbins and adjacent to the top chunk. It disappears. Chunks adjacent to the top chunk that are too large to qualify for the Fastbins, herein referred to as normal chunks, are consolidated into the top chunk, and the bins command confirms that all of the bins are empty. Next2 requests chunk B again, followed by a 20 sized chunk. We'll come back to chunk B in a moment. In the meantime, let's see what happens when we free a normal chunk that doesn't abut the top chunk. Use next to free chunk A. Now viz shows us that 3 changes have occurred on the heap. The first is that the prev in use bit of the succeeding chunk has been cleared, something that didn't happen when we freed fast chunks. We'll see what significance this has shortly. The second change is that the last quad word of chunk A's user data has been repurposed as a prev size field, which we can see matches its size, something else that didn't happen when we were dealing with the Fastbins. Note how the quad word containing the prev size field is now coloured to indicate that it belongs to chunk B rather than chunk A. This is an example of how malloc's chunks can change shape throughout their lifetime. Lastly, chunk A has been linked into the unsorted bin. The viz command has annotated that here, and we can confirm this from the output of the unsortedbin command. The unsorted bin is another of malloc's free lists. Unlike the fastbins, there is only one unsorted bin per arena. It's a doubly linked circular list that holds free chunks of any size. Because it's doubly linked, it uses both forward and backward, or FD and BK pointers, respectively. And we can see that the first two quad words of chunk A's user data have been repurposed as unsorted bin forward and backward pointers. The head of an unsorted bin exists in a heaps arena, just like the fastbins, where there are a pair of forward and backward pointers that malloc treats as if they were part of a fake chunk. The arena layout diagram in your PDF shows the location of the unsorted bin pointers, which start two quad words after the top chunk pointer. We can see them in memory by dumping the first 16 quad words of the main arena. Right now, they both point to chunk A, which is the only chunk in this unsorted bin. Chunk A's FD and BK both point to the unsorted bin chunk, which starts at the top chunk pointer. This is what I mean about malloc treating the head of the unsorted bin as a fake chunk, which is done to avoid having to treat it as a special case. Here's an example unsorted bin, with the head represented as a chunk. Each chunk's forward pointer forms a circular linked list, with the unsorted bin FD pointing to the first chunk in the bin, that chunk's FD pointing to the next chunk, and so on. The last chunk in the bin has an FD that points back to the head of the unsorted bin. Similarly, the last chunk's BK points to the previous chunk in the bin, and so on. And the unsorted bin's BK points back to the last chunk, completing the circle. Like the fastbins, newly freed chunks are added to the head of the unsorted bin, whereas, unlike the fastbins, chunks are allocated from the tail of the unsorted bin. We'll deal with allocations from the unsorted bin in a later technique. We've seen that freeing a fast chunk doesn't affect its surrounding chunks. But what happens when we free chunk B, which is adjacent to the already free chunk A, with next? The viz and unsorted bin commands tell a different story this time. Chunks A and B have been consolidated into the same larger chunk, the size field of which reads hex 120, the sum of both hex 90 sized chunks. We can also see that the 20 chunks prev in use flag is now clear, and it's adopted a prev size field indicating the previous chunk is hex 120 bytes long, matching the new chunk's size field. We see from the output of the unsorted bin command that there's still only one chunk in the unsorted bin, this new larger chunk. So adjacent free normal chunks get consolidated together. The process appears simple enough, but consider what malloc has to do in order to achieve this. When you free a chunk, it has to first check whether either adjacent chunk is available for consolidation. It does this using prev in use flags. Malloc checks the prev in use flag of the chunk being freed to see if the previous chunk is free. And to check whether the succeeding chunk is free, it has to look forward by two chunks using their size fields to check the prev in use flag of the chunk after the succeeding chunk. Once malloc has established whether either or both of these chunks are consolidation candidates, it must remove them from whichever free list they're already linked into. Otherwise, a chunk might get linked into two different lists or the same list twice. Then, malloc has to add up the total space occupied by the new, larger chunk and set the size and prev size fields accordingly. Finally, the new consolidated chunk is linked into the unsorted bin. Of most interest to us in the consolidation process is the unlinking part, where chunks being consolidated are removed from a list. For those of you with computer science backgrounds, this is basic linked lists, but it's still worth explaining. One of the benefits of doubly linked lists is the ability to easily remove an item from the middle of said list. If you want to remove an item from the middle of a singly linked list, like a fastbin, you have to iterate over that list until you find the item preceding the one you want to remove, then modify its forward pointer to skip your item. If the item you want to remove is number 1000, you have to check the forward pointers of 999 items before finding the one preceding your victim. With normal chunks, however, consolidation means that malloc has to be able to easily remove a chunk from the middle of a potentially long list. In a doubly linked list, this is easy. Let's say we want to remove this chunk from an unsorted bin with a handful of chunks in it. Follow the victim chunk's FD to the next chunk in the list and overwrite that chunk's BK with your victim's BK. Now the victim chunk is unlinked from the backward list. Next, follow the victim's BK to the previous chunk and overwrite that chunk's FD with your victim's FD. Now the victim chunk is unlinked from both the forward and the backward lists. In older versions of GLIBC, this unlinking process was done via a macro without any integrity checks on the FD and BK pointers, hence unsafe unlink. If an attacker found themselves able to tamper with the FD and BK of a chunk that was subsequently unlinked, it yielded a reflected write primitive, meaning that an attacker could select two addresses and write one near the other, and vice versa. So before we approach the modern version of this technique, which involves a little more complexity, we're going to visit the year 2000, before the introduction of NX, and leverage the unsafe unlink technique in the way it was originally designed.
The unsafe unlink is considered the original GLIBC heap exploitation technique. Developed in the year 2000 by Alexander Pesliak, aka Solar Designer, it was originally used to pwn the Netscape browser via a heap overflow.
It was also used to exploit the sudo binary the subsequent year in a FRAC article entitled Voodoo Malloc Tricks. If you haven't heard of Solar Designer, he's not only credited with the first generic heap exploitation technique, but is also the father of return-oriented programming, or ROP. Back in 1997, in the wake of Aleph-1's smashing the stack for fun and profit, he developed the first ret-to-libc attack to bypass his own non-executable stack patch. So not only did he implement NX before it was commonplace, he also developed ROP to bypass it. He then went on to develop a patch for his bypass for his patch, which involved mapping libraries into addresses with null bytes to mitigate the use of ROP in conjunction with unsafe string functions. He's an interesting guy. If you want to read more about him, FRAC published a great interview with him in 2016. So let's learn about his unsafe unlink technique. We'll begin by examining the vulnerable unsafe unlink binary. As we do every time, use checksec to see which security features it has enabled. The main difference this binary has from our previous ones is that it wasn't compiled with NX. As I mentioned in the previous video, we're taking a trip back to the year 2000, when the unsafe unlink technique was originally conceived. The advantage we have when NX is disabled is that we can write shellcode into memory that wouldn't otherwise be executable, then execute it. You'll also notice that this binary is linked against a special version of GLIBC, which is patched to behave similarly to the version this technique was designed against. So let's go ahead and load this binary into GDB, then let it run. We're provided with both a libc and heap leak, followed by the familiar numbered menu. Option 1 allows us to request only 2 chunks, which fall into the so-called small chunk range. Chunks are considered small when their size is less than hex 400, and that includes the fast sizes of hex 20 through 80. In this case, we're limited to small chunks excluding the fast range, so hex 90 through 3F0. Some of these binaries may seem needlessly restrictive in what they allow us to do with the heap, but they're designed like that to focus our attention on the technique at hand. I'll request the smallest chunk we can to keep things compact. Notice how we're not prompted for data. This time allocation and writing are done via separate menu options. In a production environment, sometimes a program might populate fields of an object immediately after requesting space for that object. Other times it might defer that write until later. Option 2 allows us to write data to chunks by index. Let's write some garbage data to our 90 chunk at index 0. Breaking in GDB and inspecting the heap shows us that, as expected, we've been allocated a 90 sized chunk to service our request for 136 bytes of memory, and the program has written our garbage data into that chunk's user data. Option 3 lets us free chunks by index. First, let's request another 90 sized chunk to stop our first chunk getting consolidated with the top chunk. Then free our first chunk and take a look at the heap. We can see the same changes we saw in the demo binary. The succeeding chunk's prev in use flag has been cleared, indicating that the previous chunk is no longer in use. The last quad word of our first chunk's user data now belongs to the succeeding chunk and has been repurposed as a prev size field, which matches its size field. Lastly, the free chunk has been linked into the unsorted bin, annotated here, the first 2 quad words of its user data repurposed as forward and backward pointers, confirmed by the unsortedbin command. The command prints some meaningless information because it's confused by the read-write-execute nature of the memory it's printing, so don't worry about that. So we can request a couple of small chunks, write data into them whenever we want, and free those chunks. Now's your opportunity to find the bug in this program, so pause the video and come back when you've found it. Did you find the bug? If not, don't worry, I'll restart my copy of the program and show you what it is. I'll request a 90 sized chunk and attempt to write more than 136 bytes into its user data. Breaking and inspecting the heap reveals that this program has an overflow bug, similar to the House of Force binary. However, this time we're not limited to overwriting just the top chunk size field. We can also target size fields belonging to other chunks. So let's request another 90 sized chunk. Inspecting the heap now shows us what we'd expect: 2 90 sized chunks, followed by a now corrupt top chunk. Let's continue and use the overflow bug again to overwrite the size field of the second 90 chunk. Break in GDB, and this time we'll need to use the dq command to inspect the heap because the corrupt size field will confuse the viz command. The mp underscore struct is used by malloc to hold a small amount of its parameter data, and we'll be seeing more of it later. For now, we'll use its sbreak base member as a quick way to find the start of the default heap, where we'll print 38 quad words of memory. We see our garbage data taking up the first chunk's user data, and that 1 quad word of it has overflowed into the succeeding chunk's size field. We can also see the top chunk's corrupt size field at the end of what was the second chunk's user data. Now, even though we can corrupt the top chunk size field with this overflow, the House of Force technique isn't viable here. We just can't request enough memory or enough chunks. So let's consider how corrupting a normal chunk's size field might benefit us. We could change its size, then free it, but to capitalize on that, we'd have to request the chunk back again, which we can't do due to the 2 request limit imposed by this program. But what if we left the size alone and instead just changed the flags. Consider what would happen were we to clear the second chunk's prev-in-use flag. We know that the prev-in-use flag is used by malloc to determine whether a previous chunk is a candidate for consolidation. In this case, clearing the second chunk's prev-in-use flag would indicate to malloc that were we to free the second chunk, the first chunk would be a consolidation candidate. We also know that the consolidation process would involve unlinking the first chunk, but the first chunk isn't really free, so it isn't linked into a free list, and therefore has no forward or backward pointers. However, this is our opportunity to provide them. And remember, an unsafe unlink operation on attacker-controlled pointers yields a reflected write primitive. So let's close GDB, make a copy of the pwntools template Python script, and open it in your editor of choice. Scroll to the bottom, where we can see some example uses of the helper functions. The malloc function just takes a request size argument this time. There's an edit function that takes the index of the chunk you want to edit as the first argument, and the data you want to write as the second. Lastly, there's a free function that takes an index argument. There's also a shellcode variable which holds some execve bin sh shellcode compiled by the shellcraft module that comes with pwntools. We'll make use of this later. We're going to start by doing what was suggested earlier. Corrupt a chunk's size field by clearing its prev-in-use flag. Begin by clearing everything except the shellcode and requesting two 9-0 sized chunks, although you could use any size the program accepts. I'll label mine chunks A and B. Remember that an easy way to request a chunk of specific size is to subtract 8 from the size you want. Hence, my request size is of hex 88. Run your script with the GDB and no ASLR options to check that everything is as expected. After breaking, viz shows us that we have two 9-0 size chunks on the default heap, both of which have their prev-in-use flags set. Return to your editor. Now we're going to leverage the overflow bug to overwrite chunk B's size field. We want to keep the size the same, but clear its prev-in-use flag. Because chunk A has 136 or hex 88 bytes of user data, I'll need to write that many bytes of garbage into it first. You'll need to write however many bytes of user data your first chunk holds. Then we'll replace the next chunk's size field, which in my case currently holds the value hex 91. So I need to pack a hex 90 value here, keeping the size the same whilst clearing the prev-in-use flag. You'll need to apply the same change to your second chunk's size field. Running our script with the debugging options and inspecting the heap shows us that it's had the intended effect. Chunk B now has a size field of hex 90 rather than hex 91, and the last quad word of chunk A's user data is now considered part of chunk B, specifically its prev size field. So what would happen if we tried to free chunk B now? Well, malloc would check its prev-in-use flag, see that it was clear, and attempt to consolidate chunk B with chunk A. To find the start of chunk A, malloc needs to use chunk B's prev size field. But right now, that field is populated with garbage. So malloc would undoubtedly cause a seg fault whilst trying to access memory at that address, minus hex 595959, etc. So let's return to our editor and make some more changes. Let's prepare some variables ahead of time to make our lives easier. Soon we'll have to forge a pair of forward and backward pointers for our reflected write, so let's create placeholders for those now. We'll need to set a prev size field that guides malloc to the start of chunk A. In my case, this value is hex 90, which is what would legitimately be written there if we had freed chunk A. Use the size of your first chunk here. To help clarify things, let's also turn our fake size field into a variable. We need to write the FD and BK into the first two quad words of chunk A, followed by enough garbage to take us up to the prev size field. We can use the p8 or pack8 function here to write null bytes rather than printing characters, which can make things a little less cluttered when viewing memory dumps. Then we'll append our prev size field and fake size fields. Once you've made those changes, run your script with the usual options and inspect the heap. We can see our forged FD and BK at the start of chunk A, chunk B's cleared prev in use flag, and this time we have a sane prev size field for malloc to use. Now, if we were to free chunk B, malloc would check its prev in use flag, see that it was clear, attempt to consolidate chunk B with chunk A, read our forged prev size field, and subtract it from chunk B's address to successfully find the start of chunk A. Next, it will attempt to unlink chunk A from whichever free list it's linked into. It's at this point that malloc will perform the unlink procedure on our forged FD and BK, giving us that reflected write primitive. Malloc will follow our FD to what it believes is another chunk, and overwrite that chunk's BK with our BK. Then malloc will follow our BK to what it also believes is another chunk, and overwrite that chunk's FD with our FD. For this to work, both addresses we supply must point to writable memory, which means if we try to overwrite the free hook with the address of system, for example, the second half of our reflected write will attempt to write the address of the free hook into the system function, causing a segfault as it tries writing to non-writable memory. Fortunately, it's the year 2000, and our writable memory is also executable. Full railrow is still enforced, however, so we need to target the malloc hooks for our attack to succeed. We have a heap leak, and we can write shellcode onto an executable heap. So what's stopping us from using our reflected write to overwrite the free hook with the address of our shellcode? Let's try it. Return to your editor, where the first thing we'll do is write our shellcode into chunk A. Don't forget to amend the amount of garbage we write into chunk A to account for the shellcode. Next, we'll focus on the first half of the reflected write, in which our BK will be copied to where our FD points, plus hex 18. So let's set our BK to the address of our shellcode on the heap, which starts in the first chunk, just after our forged FD and BK, so heap plus hex 20. We want to copy this BK into the free hook. That way, when we attempt to free another chunk after the unlinking has taken place, our shellcode will be executed instead. So let's point our FD at the free hook minus hex 18 to account for the fact that malloc will treat whatever our FD points to as a chunk, and overwrite its BK, which is 24 or hex 18 bytes after the start of that chunk. Now we'll run our script with the usual debugging options, break, and inspect the heap where we can see our forged FD and BK at the start of chunk A. Printing the address of the free hook confirms that our FD points 24 bytes before it, and our BK holds the address of our shellcode. To trigger the unsafe unlink attack, all we need to do is free chunk B. Malloc will check its prev in use flag, which we've cleared via the overflow bug, and attempt to consolidate it with chunk A. The prev size field that we supplied will be used to find the start of chunk A, which will then be subject to the unlinking process. Our forged FD will be followed, and our BK will be copied over the BK of the chunk at the destination, which overlaps the free hook. So let's continue, switch windows to the program, free chunk B at index 1, triggering the unsafe unlink, then return to GDB, break, and inspect the heap again. It looks like all that's left of our two chunks is the top chunk. Remember that so-called normal chunks can not only be consolidated with each other, but with the top chunk too. Since chunk B bordered the top chunk, it was first consolidated with chunk A, then consolidated into the top chunk afterwards. But that doesn't mean our unsafe unlink didn't work. Dumping the memory that the free hook points to reveals that it's pointing to our shellcode on the heap. Great, next time we free a chunk, our shellcode will be executed. There's just one thing we haven't accounted for, and that's the second half of the unlinking procedure, in which our BK was followed and our FD copied over the FD at its destination. And we can see the outcome of that process here, where our FD has been written into the middle of our shellcode. This leaves us with just 16 bytes of shellcode to deal with this corruption. Fortunately, by disassembling the first part of our shellcode with the U command, we see that this shellcode already accounts for this by using its first 2 bytes to jump over the corruption, after which the actual shellcode starts. All that's left to add to our exploit is one line to free chunk B, triggering the unsafe unlink, and another line to free chunk A afterwards, executing our shellcode via the free hook. So let's return to our editor and make those final changes. While you're doing that, notice the jump instruction prepended to the shellcode that dealt with the side effect of the unsafe unlink. Once you're ready, run your exploit script under production conditions, and you should get a shell. We just leveraged the original unsafe unlink technique. In summary, we requested 2 chunks, A and B, and took advantage of a heap overflow to clear the prev-in-use flag on chunk B that should otherwise have it set. In this case, the overflow was a whole quad word, but it could just as easily have been a single byte or even a single null byte if the size field already had a least significant byte of 0. When we freed the corrupt chunk B, malloc determined that because its prev-in-use flag was clear, its previous chunk was a candidate for consolidation. Consolidation involves unlinking the candidate or victim chunk from its free list and adding its size to the chunk being freed. To find the candidate chunk, malloc uses the prev size field of the freed chunk. Prev size fields are formed from the last quad word of user data belonging to the previous chunk. We were able to correctly populate chunk B's prev size field because chunk A wasn't really free, so we still controlled its user data. Next, malloc attempted to unlink chunk A, and because we still controlled its user data, we were able to provide forged FD and BK pointers for the unlink process to operate on. We pointed our FD at the free hook, -24, and our BK at some shellcode we had written onto the heap. The unlink process followed our FD and copied our BK over the free hook. It then followed our BK and copied our FD 16 bytes into our shellcode, which we had to deal with by providing a jump instruction to jump over it. Finally, we triggered a call to free, which was redirected via the free hook to our shellcode on the heap, giving us a shell. Don't forget that the only reason we were able to use shellcode this way is because it's the year 2000. Nevertheless, if you're dealing with IoT or embedded devices, you may find that NX is not enabled, even in the present day. As usual, you can download a working exploit script, complete with comments, from this section's resources. If you want to refresh your memory on the unlinking process, you can refer to the unlinking section of the PDF. It's worth noting that we used so-called backward consolidation against this binary, where the forged FD and BK are held in the chunk behind the chunk being freed. There does exist a forward consolidation variant of this technique, in which the forged FD and BK reside in the succeeding chunk. This variant was used in 2001 to exploit the sudo binary. But if you're tired of life in the early 2000s, then join me in the next video where we return to the present day to show how this technique can still be leveraged against modern versions of GLIBC.
So how does a technique from the year 2000 hold up against modern versions of GLIBC? We're about to find out in the safe unlink technique.
Navigate to the safe unlink directory. We're already familiar with the malloc internals required to leverage this technique, So we'll crack straight on with the vulnerable safe unlink binary, starting with our usual drills. Checksec shows us that we're firmly back in the present day, with NX enabled, alongside the usual stack canaries and full rel row. AMD introduced hardware NX support to their consumer desktop processors in 2003, followed by Intel in 2004, although they called it XD for execute disable. We also see that the binary is linked against GLIBC version 2.30, compiled without Tcache support. We'll continue our usual investigation of the binary by loading it into GDB and running it. This time we have a libc leak, but no heap leak. Other than that, the menu looks familiar. In fact, with the exception of the target option, this program behaves identically to the unsafe unlink binary. The only differences are those we've already noted, that NX is enabled, and the glibc version it's linked against is more modern. We're still only able to request up to 2 chunks with option 1, in the small chunk range only, excluding fast sizes. We're able to write to those chunks user data with option 2, and free them by index with option 3. The target option works as expected, and as usual, the target data resides in the data section of the binary, which is non-position independent. If I request a hex 90 sized chunk and attempt to write too much data into it, inspecting the heap reveals that the bug is also identical to the unsafe unlink binary, an overflow into the succeeding chunk's size field. We'll start, as we usually do, by building an arbitrary write primitive, which we'll use to overwrite the target data. And we are of course going to leverage the unlinking process to do this. There are just 2 mitigations that stand in our way. The first is of course NX. In the unsafe unlink technique, we were able to redirect execution to our shellcode stored on the heap. The presence of NX means that we can no longer do this because the heap, along with all other data regions, will be marked as non-executable. This greatly restricts the number of viable targets for the reflected write primitive we get from hijacking the unlinking process. Recall that one prerequisite of the reflected write is that both addresses we supply must point to writable memory. For example, if we write the address of system to the free hook, the reflected write will also attempt to copy the free hook address into the system function, which is marked as non-writable. So we'll need to rethink our forged FD and BK pointers. The second mitigation we had to deal with is in the unlink macro itself. Note that in later versions of glibc, the unlink macro became a function called unlink chunk, although it still does the same job. I'll use the term unlink macro/function interchangeably. Shown in blue is the unlink macro as it existed in the year 2000. This is what we leveraged in the unsafe unlink technique. All it does is copy a chunk's FD and BK in that reflected write pattern. Shown in red is how the unlink function exists today. Calls to the malloc printerr function, highlighted in bright red, are part of malloc's exploit mitigations, and what cause a process to abort when their preceding check fails. Of interest to us is the second check, known as the safe unlinking check. It's there to ensure that the chunk being unlinked is really part of a doubly linked list. Let's break it down. P represents the victim chunk. FD and BK are its forward and backward pointers, respectively. The process will abort if either of the following are true. On following the victim's FD, the BK at that location does not point back to the victim chunk. Or, on following the victim's BK, the FD at that location doesn't point back to the victim chunk. You may have noticed that we could pass the safe unlinking check by simply setting both our forged FD and BK to the address of the chunk being unlinked. However, this would not only require a heap leak, which we don't have in this scenario, but would render the reflected write useless, since we'd just be overwriting our own data with values that already exist. We need to come up with a different target for our reflected write, one that passes the safe unlinking checks and yields a useful primitive. So let's learn a bit about how this binary works. One of malloc's many small optimizations is that it doesn't keep track of allocated chunks. It maintains pointers to its heap's top chunks and free chunks in their respective arenas, but when a chunk is allocated to a thread, that thread is expected to keep a reference to the chunk until it returns it to malloc via functions like free. This means that a program must store pointers to every chunk it's been allocated somewhere, whether it keeps them on the stack, its data section, or even on the heap itself. The vulnerable binaries we've dealt with so far keep their chunk pointers on the stack, where we are unable to tamper with them through lack of a stack leak. This binary, however, keeps its chunk pointers in its data section, in an array labelled m_array, which is just an arbitrary name I've given it. This is by no means uncommon. Even if a program keeps most of its chunk references on the heap itself, it still needs to store the pointer to that initial heap memory on the stack, or, if it wants that space to be more widely accessible, its own data or BSS sections. Because this binary is non-position independent, we know the address of m_array at runtime. Printing the array shows that it's made up of pointers to chunks, followed by the size of the request that chunk was allocated for. These pointers are used by the program when the edit and free options are selected. Earlier, we noted that one way to pass the safe unlinking checks was to use pointers to the chunk being unlinked. And here we have a pointer to that chunk. If we forged our FD and BK such that this pointer in m_array became both the BK of the chunk pointed to by our FD and the FD of the chunk pointed to by our BK, that would pass the safe unlinking checks. Furthermore, the reflected write would have the effect of overwriting the targeted m_array entry with our forged FD, which is the address of itself -24. Once that's happened, the edit option could be used to overwrite m_array entries with more control, leading to an arbitrary write. Now, there's clearly a lot of moving parts to this technique, so we're going to take it one step at a time. Close GDB, make a copy of the pwntools template, and open it in your editor. Scroll to the bottom, and you'll see that we're starting more or less where the unsafe unlink left off. We begin by requesting two 9-0-sized chunks, A and B. Then we fill chunk A with forged chunk metadata and use the overflow bug to clear chunk B's prev in use flag. There's also an example of how the address of m_array can be accessed via elf.sim.marray. Let's clear out the first few lines, leaving just the important stuff. Now we can point our FD at m_array, -24, so that the BK of the chunk malloc will think is there overlaps the first m_array entry. We'll give our BK the same treatment, pointing it at m_array -16 to overlap the first entry with the imaginary chunk's FD. Run your script with the usual options: break, viz, and dump quad words at m_array -2. We see the first entry in m_array here, pointing to chunk A's user data. Our forged FD points here, making that first entry that imaginary chunk's backward pointer. So now the BK of the chunk pointed to by the victim's FD points back to the victim. That's the first half of the safe unlinking check. Our forged BK points here, making the first M-array entry that chunk's FD. Now, the FD of the chunk pointed to by the victim's BK also points back to the victim, which completes our safe unlinking checks. But we're forgetting something important. Malloc uses metadata pointers when dealing with chunks, not pointers to user data. So the FD and BK of those imaginary chunks we've overlapped with M-array are pointing 16 bytes after where they need to be to pass the checks. We can confirm this by freeing chunk B, at which point we receive the error message we saw in the unlink function. And we can see the last call made from that function was right after failing the safe unlinking check. So how do we solve this problem? Well, recall how we directed malloc to unlink chunk A in the first place. We forged a prev size field that led malloc to the start of chunk A. So what's stopping us from subtracting 16 bytes from our forged prev size field to convince malloc that the chunk it needs to unlink starts at chunk A's user data instead? Return to your editor and let's make that change. Decrease your fake prev size field by 16 bytes, and we'll need to add some more metadata into chunk A, since we're now forging an entire fake chunk inside it. Add 2 quad words to your payload. The first is an unused prev size field. The second is the size field of our fake chunk. We actually need to set this correctly to hex 80, as the version of GLIBC we're dealing with will abort if it doesn't match the prev size field of the chunk that led malloc to our fake chunk in the first place. We take a closer look at GLIBC's so-called size versus prev size checks in part 2 of the HeapLAB course. Lastly, we need to decrease the amount of garbage between our BK and prev size field to account for the new fields. Let's run our exploit script with the usual debugging options and see if we've set up everything correctly. Inspect the heap, then with a little gdb foo, we can see what malloc sees when it follows our forged FD. This line simply casts our fake chunk as a malloc chunk struct and follows its forward pointer. It shows us that the BK of the chunk at that address points back to our fake chunk, this time to the start of the chunk rather than its user data. And this is enough to pass the first half of the safe unlinking check. Following our forged BK shows that the FD of the chunk at that address also points back to our fake chunk, which is enough to pass the second half of the safe unlinking check. This time when we free chunk B, GLIBC doesn't abort, and we can return to GDB to see the damage we've done. Avoid using the viz heap chunks command at this point. We've corrupted the heap and it will get confused. Instead, use dq and the sbreak base trick to dump some memory at the start of the default heap. The top chunk command reveals that we've consolidated chunk B not only with our fake chunk, but with the top chunk as well. And because our fake chunk was consolidated, it was also unlinked, meaning that our reflected write must have worked. Dumping the memory surrounding M-array shows the outcome of this. We can see the first entry in M-array pointing not to the heap anymore, but to 24 bytes before itself. This is the result of the second half of the unlinking process, in which our forged BK was followed and our forged FD was copied over the FD at the destination. Notice how our FD and the first M-array entry are identical. Now we can use the edit option to write to the chunk at index 0 of M-array, which allows us to overwrite M-array itself a second time with our own controlled data. Rather than doing that manually, let's add it to our exploit script. We'll need to start by freeing chunk B, triggering the consolidation with our fake chunk and unlinking it. At this point, the address at index 0 of M-array points near itself, thanks to our reflected write. So we'll use the edit option with an index of 0 to overwrite that address a second time. We'll need to send 3 quad words of garbage because that M-array entry points 3 quad words behind itself, followed by the address we want to replace it with, in this case, our target data. Now the first entry in M-array points to our target, and we can use the edit function again, select index 0, and overwrite the target data. Running our script under production conditions and selecting option 4 confirms that we've successfully turned the safe unlink technique into an arbitrary write. In summary, we requested 2 chunks A and B and leveraged an overflow bug in this binary to clear the prev-in-use flag on the allocated chunk B. We also prepared fake chunk metadata in its previous chunk, chunk A, including a size field, forward and backward pointers, and a prev size field. When we freed chunk B, its clear prev-in-use flag indicated to malloc that the previous chunk was free, even though it wasn't, and therefore a candidate for consolidation. Malloc used our forged prev size field to find the start of the previous chunk so it could unlink it prior to consolidation. We set our prev size field to the actual size of the previous chunk minus 16, making it appear as though the previous chunk started at the first quad word of chunk A's user data, where we'd prepared the rest of our fake chunk metadata. Malloc then performed its safe unlinking checks on our fake chunk. First, it followed our FD and checked that the BK at the destination pointed back to our fake chunk. We passed this check by aligning our FD address such that the BK at its destination overlapped a pointer back to our fake chunk. Next, malloc followed our BK and performed the same check on the FD at its destination. We passed this check using the same trick of aligning our BK address such that the FD at its destination also overlapped the same pointer to our fake chunk. Once our fake chunk passed the safe unlinking checks, malloc unlinked it. It followed our FD and copied our BK over the BK at its destination. Then it followed our BK and copied our FD over the FD at its destination. This had the effect of overwriting the pointer to our fake chunk with its own address, minus 24. Because the program was using that pointer for write operations that we controlled, we were able to leverage it to overwrite that pointer again, this time with controlled data. We overwrote the pointer with the address of our target data, allowing us to finally overwrite the target. Now, this technique can be difficult to understand the first time, especially the part where we pass the safe unlinking checks. So don't hesitate to replay this video if you need to. There's also a commented solution script available from this lecture's resources. Now that we've leveraged the safe unlink technique for an arbitrary write, let's wrap things up by dropping a shell. The arbitrary write primitive we've developed doesn't have any strings attached, so this should be straightforward. If you're confident you can finish this exploit on your own, now is a good opportunity to pause the video and do so. If we swap the address of our target for the address of the free hook when overwriting the first M-array entry, our next attempt to edit the chunk at index 0 will allow us to overwrite the free hook, which we can replace with the address of the system function. The only problem with that is when we free the only chunk we can at index 0, that pointer will be the address of the free hook, so we can't write a bin sh string there. But instead of using a 1 gadget, why don't we just point this M-array entry 8 bytes before the free hook? That way we can write our bin sh string before the free hook, and it conveniently takes up exactly 1 quad word, then continue writing, clobbering the free hook itself. Let's test our exploit under GDB to see if we've got everything in place. It looks like the free hook has been overwritten with the address of the system function, and the first entry in M array, which has yet to be freed, points to the string bin sh. All that's left to do is free the chunk at index 0. The free hook will redirect free to system, and the argument passed to it will be a pointer to the string bin sh. Let's return to our editor and add this final line to our exploit. Now when we run our exploit under production conditions, we get a shell. If you need to clarify anything we've learned in this video, or just refresh your memory on this technique later, there's a second commented exploit script that drops a shell, again available from this lecture's resources. And don't forget to browse the PDF if you need a reminder of any malloc internals. And that's the safe unlink technique, the modern equivalent of the unsafe unlink. To leverage it, we had to be able to clear the prev in use bit of an allocated chunk, for which we used an overflow bug. And we had to know the address of a pointer to a chunk. In this case, we used one stored by the program in its data section. Join me in the next video, where we'll start our journey towards learning the House of Orange technique, which is without a doubt one of the most beautiful and complex heap exploitation techniques out there.
We're going to learn a technique known as the House of Orange. It was developed in 2016 by Angel Boy, and it is a beautiful end-to-end heap exploitation technique. By end-to-end, I mean that it's designed to drop a shell.
It can be broken down into 3 phases, which we're going to learn in reverse order. If we covered each phase as we approached it in our exploit, then the links between them wouldn't be as clear. So let's start with phase 3, which is the part where we drop a shell. Until now, we've been leveraging the malloc hooks to get our shells. But the House of Orange uses something known as file stream exploitation. Some call it file stream oriented programming, and it's just a way of taking advantage of a fundamental GLIBC feature to achieve, amongst other things, arbitrary code execution. So, when you're ready to begin, start the next video. In this video, we'll learn about file stream exploitation, starting by answering the question, what is a file stream? When you request access to a file on Linux, your process is issued with a file descriptor, or FD for short, not to be confused with the forward pointer FDs we've been dealing with so far. File descriptors are positive integers that your process can use as a handle to a resource. But dealing with files via file descriptors can be cumbersome. You can read and write, but often how we want to deal with files is more nuanced. That's where GLIBC's file streams come in. They're wrappers around file descriptors that provide some quality of life functionality like buffered I/O and undo, for example. They take the form of I/O file structs in memory. These are what functions like fopen return pointers to. So let's take a look at the I/O file struct. One way to quickly inspect GLIBC structs without having to trawl the source code is to use GDB. If we load a binary into GDB, anyone will do, so I'll pick our friend bin sh, and issue the start command to ensure its libraries get loaded, we can use the ptype command to inspect GLIBC's types. You can pass the /o option to print the offset of each struct member, and don't forget to use the struct keyword when inspecting structs. In this case, I/O file structs are type deft to file, so we can shorten this command if we want. pwntools allows us to shorten this command further using the dt or dump type command, which also gives us neater output. Be aware that at the time of recording, the dt command requires you to wrap the type in quotes if there's a space in it. For example, dt quote struct IO file quote. As I mentioned, IO file structs are wrappers around file descriptors. The file descriptor in question is held in the FileNo member. You can see that file streams consist primarily of character buffers, which are used to support those features I mentioned like buffered I/O. We'll briefly cover some of the other fields that will be of interest to us during this course. There's a flags member at the start of the struct that determines the state of the file stream. There's also a chain member. Its type indicates that it's a pointer to another I/O file struct. These chain members form the links of a singly linked, non-circular list of all the open file streams in a process. The head of that list is a symbol called IO list all. Every time a new file is opened by a function like fopen, an IO file struct is created on the heap and is linked into the head of the IO list all list, sort of like a fastbin for files. The mode field can be used to disable the file stream. Its usefulness will become clear later. For now, let's revisit IOListAll and note that its type is IOFile+. It wouldn't be GLIBC without a certain amount of indirection, and the IOFile+ struct is just a wrapper around the IOFile struct that adds a vtable pointer to it, as we can see from the output of this dt command. If you're comfortable with what vtables are and how they work, you can skip this next part. For those of you unfamiliar with vtables, they're one way of implementing polymorphism in object-oriented languages like C++, and we'll use an example to get familiar with them. Say we have a class, car, that has a function that enables it to accelerate. When we derive further classes from car, for example, Skoda and Ferrari, we might want those different cars to accelerate at different rates. So we make accelerate a so-called virtual function, simply meaning that Skoda and Ferrari can override it with their own implementations. When a car's accelerate method is called directly from the car object, the call can go straight to the appropriate version of accelerate. But consider a function that takes any type of car as an argument, then calls its accelerate method. This function could end up calling a Skoda's accelerate method or a Ferrari's, and there's no way for the compiler to tell which type of car it's going to receive at runtime. This is known as polymorphism, and languages like C++ often don't specify how it should be implemented, but one solution is to use vtables. Now, I am simplifying somewhat, but the basic principle is to give each class that uses virtual functions a virtual function table, or vtable. Typically, there's a single vtable per class, and each instantiated object of that class gets a pointer to its appropriate vtable. For example, our Skodas and Ferraris could each get a vtable that looks like this. The third entry in the Skoda vtable holds the address of the Skoda accelerate function, and the third entry in the Ferrari vtable points to the Ferrari accelerate function. Every Skoda or Ferrari object would also get a vtable pointer to its vtable. Now, when the function I described earlier needs to call the correct version of a car's accelerate method, all it has to do is follow the object's vtable pointer and call the third entry in that vtable. If you've ever exploited C++ binaries, you may have practiced vtable hijacking. For those of you who haven't, vtable hijacking is simply the process of overwriting an object's vtable pointer using a bug like an overflow, then pointing it to a fake vtable that you control. In this scenario, we could set the third entry of our fake vtable to the address of a OneGadget. Then, the next time this object's accelerate function was called, we'd get a shell. So if vtables are used in object-oriented languages like C++, what are they doing attached to IO file structs in the GNU C library? Well, the GNU C and C++ libraries are tightly linked. If you debug a C++ program on Linux, you'll notice that alongside the C++ standard library, the C standard library has also been loaded. This is because the GNU C++ library uses some of the C library's low-level functionality, rather than re-implementing it. For example, if you debug a C++ program that opens a file and set a breakpoint on the C library's fopen function, you'll notice that the C++ standard library is actually calling into the C standard library to perform the low-level file operations. This is also true of C++ methods like makeShared and makeUnique, which both use the C library's malloc functions under the hood. In the case of IOFile+ structs, they're given a vtable pointer to be compatible with the C++ streamBuff class. And regardless of the reason, this makes GLIBC's file streams vulnerable to vtable hijacking, a form of file stream exploitation, and the method we're going to use to get our House of Orange shell. So file streams are clearly valuable targets, and since new file streams are created on the heap, they're potentially vulnerable to the different heap bug classes, such as overflows and double freeze, that we've leveraged so far. But can we only target them when a process opens new files? The answer is no. Any process that uses the GNU C library will always have at least 3 file streams: standard in, standard out, and standard error, collectively known as the standard IO file streams. Even a program that prints no output and accepts no command line input will have the standard IO file streams present in the data section of its copy of GLIBC. The same is true of more complex programs that use a GUI. I'll use Firefox as an example, since Ubuntu Linux comes with it installed. Attaching GDB to Firefox and printing the value at the head of the IOListAll list shows that standard error was the last file to be opened, represented by the standard error file stream. Following that file stream's chain pointer takes us to the standard out file stream, then to the standard in file stream, where the chain terminates. The xinfo command shows us that the standard out file stream, represented by an IOFile+ struct, resides in GLIBC's data section, along with standard in and standard error. So even if our binary doesn't open any files, or use the standard IO file streams, they'll still be present for us to leverage file stream exploitation against. That's phase 3 of the House of Force. We're going to corrupt a file stream's vtable pointer, or perhaps even inject our own fake file stream. Then, when one of those file stream's member functions is called, execution will be redirected via our fake vtable, gaining us arbitrary code execution. Join me in the next video, where we'll be learning about the second phase of the House of Orange, the Unsortedbin attack. Let's move forward, or back, to the technique we're going to leverage in phase 2 of the House of Orange. It's known as the Unsortedbin attack. To understand it, we need to cover some more malloc internals. This time, we're going to flesh out our understanding of the unsorted bin and its relationship to malloc's other bins. We know that a number of fates may befall a chunk when it's freed. If it qualifies for one of the Fastbins, it may get linked directly into that Fastbin. If it's too large for the Fastbins and borders the top chunk, or is consolidated with a chunk that borders the top chunk, it gets consolidated into the top chunk. If it's too large for the Fastbins and doesn't border the top chunk, it gets linked into the unsorted bin, possibly after consolidation. Or else it might get linked into the T-cache, which we'll cover in part 2 of the HeapLAB course. But there are 2 more bin collections that aren't populated directly by the free function. Instead, Chunks from the unsorted bin are moved into these bins through a process known as sorting, which occurs during calls to malloc. These bins are called the small bins and the large bins. You can see the position within their arena these bins occupy from the arena layout diagram in the PDF. The small bins start straight after the unsorted bin, and the large bins start after the small bins. The small bins are a collection of doubly linked circular free lists. There are 62 small bins from size hex 20 all the way to 3F0, overlapping the fastbin sizes. Small bins are first in, first out, much like the unsorted bin, but each of them only holds chunks of a specific size, like the fastbins. The large bins are also a collection of doubly linked circular free lists, although they hold chunks within a range of sizes from hex 400 and up. The large bins operate a little differently, using something called a skip list, and we'll cover those in part 2 of the HeapLAB course. The sorting process responsible for moving free chunks from an unsorted bin into the small or large bins begins when malloc searches an unsorted bin whilst trying to service a request. If you browse to the malloc flowchart section in your PDF, you'll see that the unsorted bin is searched when a request size falls outside that of the tcache, fastbins and small bins range, or it's in one of those ranges but the target bin is empty. You'll recall from the unsafe unlink technique that the unsorted bin is a doubly linked circular list containing free chunks of varying sizes. Newly freed chunks are added to the head of the unsorted bin, but during requests, malloc searches it from back to front. Allocations from the unsorted bin are exact fit, meaning that if you request a hex 90 sized chunk, and malloc ends up searching the unsorted bin for one, it will only return a 90 sized chunk, even if larger ones are available. But what does malloc do with the other unsorted chunks that it encounters during the search for your chunk that don't match the request size? These chunks are sorted into their respective small or large bins. For example, let's say our unsorted bin contains 4 chunks, with sizes hex 100, 90, 400, and 230. If we make a request for a 90 sized chunk when the 90 tcache bin and small bin are empty, malloc will start searching the unsorted bin from back to front. So it follows the BK at the head of the unsorted bin stored in an arena to the last chunk in the list. That chunk isn't an exact fit, it's not 90 sized, so malloc sorts it into the 230 small bin. It continues to search backwards through the unsorted bin, encountering a 400 chunk. That isn't an exact fit either, so malloc sorts it into the 400 large bin. The search continues backwards through the unsorted bin, this time encountering a 90 chunk, which is an exact fit, so malloc allocates it to service the request, and the search ends. There is one exception to the exact fit rule that we'll cover later, known as the last remainder, but for now consider all allocations from the unsorted bin to be exact fit. When each of the chunks in that last example was sorted or allocated, they had to be unlinked from the unsorted bin. We dealt with unlinking in the unsafe unlink technique, where we saw the unlink macro being employed. But in this case, malloc doesn't need to use the unlink macro or function, because malloc not only knows which bin the sorted or allocated chunk is in when it unlinks it, but which position in that bin it occupies. The unlink process can be streamlined into what malloc refers to as a partial unlink. The process is simple. The victim chunk's FD is ignored because it will always point to the head of the unsorted bin, since the victim is always the last chunk in the unsorted bin. The victim's BK is followed, and the address of the unsorted bin is copied over the FD at the destination, which is enough to remove the victim chunk from the forward list. The victim is then removed from the backward list by copying its BK over the unsorted bin's BK. The reason that unsorted bin partial unlinks are of interest to us is because, unlike the unlink macro and unlike partial unlinks from the small bins, unsorted bin partial unlinks are not subject to any integrity checks, at least not in the version of GLIBC we're targeting in the House of Orange. And this forms the basis of the unsorted bin attack. The premise is simply to leverage a bug to tamper with an unsorted chunk's BK, then trigger a partial unlink. The primitive we get from this is writing the address of the unsorted bin to a location of our choosing, potentially leaking the arena by subsequently reading that value, or, in the case of the House of Orange, something far more devious. We're going to practice an unsorted bin attack, not against the House of Orange vulnerable binary, but in something I call the malloc testbed. Navigate to the malloc testbed directory and list the contents. There's a binary, template script, and a second script named change_glibc_version.py. I'll run the malloc testbed binary under GDB to show you what it's for. Its output is similar to the other vulnerable binaries, with some leaks followed by a menu, and the purpose of the malloc testbed is to provide a binary against which we can test different techniques or ideas and learn malloc internals in a practical way. It leaks its libc, heap, and marray address, and you can request up to 64 chunks of any size. You can free those chunks, edit their contents, read data from them, and list them. There are also a lot of bugs. You can double free chunks. You can even free arbitrary addresses. The edit and read options can be used even after a chunk has been freed, which is a bug class known as a read or write after free. And lastly, the edit option has a large overflow bug. If I break in GDB and issue the vmmap command, we can see that the malloc testbed is linked against GLIBC version 2.27. But what if we want to test an exploit against a different version of GLIBC, because it behaves differently or has more or less mitigations? This brings us to the most useful feature of the malloc testbed, the change_glibc version script. And it does exactly what it says it does. You can use it to change which version of GLIBC the malloc testbed uses. We'll see shortly that our House of Orange binary is linked against GLIBC version 2.23. So let's change the malloc testbed version to match. That way we won't get caught out by any mitigations we didn't account for. Just like the other vulnerable binaries, the malloc testbed comes with a template script, which we're going to copy and edit to practice the unsorted bin attack. As usual, the script has helper functions for every menu option. Feel free to play with those later. Right now, we're going to stick with the malloc, free, and edit options. Clear the lines starting with log.info and the call to edit, but keep everything else. Unsurprisingly, the first thing we'll need to leverage an unsorted bin attack is a chunk in the unsorted bin. This example script already sets that up for us by requesting chunk A, a 90 sized chunk, followed by a 20 sized chunk, then freeing chunk A. Chunk A is too large to qualify for the Fastbins, so is linked into the unsorted bin. Chunk B is there to guard against consolidation with the top chunk. If we run the script now with the GDB and no ASLR options, break, and inspect the heap with viz, we can see chunk A at the start of the heap, linked into the unsorted bin, which we can confirm with the unsortedbin command. We know that an unsorted bin attack starts with overwriting an unsorted chunk's backward pointer, or BK, and the malloc testbed has lots of bugs that could allow us to do that. The easiest to leverage right now is the write after free bug, which allows us to write into chunk user data after a chunk has been freed. Bugs like this can manifest when a program doesn't properly dispose of pointers to free chunks, for example. So let's return to our editor and add a call to the edit helper function. We'll edit chunk A after it's free, overwriting its unsorted bin metadata. You'll recall from the slides that the partial unlink procedure we're taking advantage of ignores the victim's FD, so we could write any value there. The next value we send will overwrite chunk A's backward pointer. Let's use the address of the heap minus 16. The idea is that when chunk A is subject to a partial unlink, malloc will follow our forged BK and copy the address of the unsorted bin over the FD at its destination, which is why we subtract 16. The outcome of our unsorted bin attack will be that the address of the main arena's unsorted bin is written into the first quad word of the heap. We'll target that location not because it's useful, but because it should always be null under normal circumstances, making it easy to confirm our attack was successful. To trigger the unsorted bin attack, we need chunk A to be subject to a partial unlink. The easiest way to do that is just to allocate it directly from the unsorted bin by making a request for a chunk that matches its size. While it's true that requesting a different size would still subject chunk A to a partial unlink, as it was sorted rather than allocated, remember that a side effect of the unsorted bin attack is that our forged BK is copied over the unsorted bin's BK. This means that as malloc continues to search the unsorted bin after sorting our victim chunk, it will follow our forged BK and try to determine whether the chunk at its destination could be used to service the current request. This can lead to general protection faults as malloc tries to read unmapped memory or even trigger one of malloc's exploit mitigations that performs size sanity checks during unsorted bin searches. So we'll stick with allocating chunk A to trigger our unsorted bin attack. Once you've made those changes, run your script with the debugging options, break, and inspect the heap. We can see our garbage FD, which didn't cause any problems even though it points to unmapped memory, followed by our forged BK, which points 16 bytes before the start of the heap. And in the first quad word of heap memory is the address of the main arena's unsorted bin, written there as a result of our unsorted bin attack. We can confirm this with print &main_arena.bins. Malloc doesn't use different symbols for its bins, they're just kept in a large array called bins and accessed via macros. The unsorted bin FD and BK are the first entries in the bins array, making the address of the unsorted bin chunk, remember that malloc treats its bins like chunks, 16 bytes before the bins array, which matches the value written by our unsorted bin attack. So, in summary, if you're able to tamper with an unsorted chunk's BK, then partially unlink that chunk by allocating or sorting it, you can write the address of that unsorted bin to an arbitrary location, and the whole process is known as an unsorted bin attack. The primitive we get from it sounds benign, but it can be used to leak an arena's address. If that arena happens to be the main arena, that's also a libc leak. However, we're going to put it to a different use in the House of Orange. Be aware that the unsorted bin attack has a mitigation introduced in GLIBC version 2.28. If you want to review the unsorted bin attack at any time, you can download a copy of my script from this lecture's resources. There's also a brief overview of unlinking, including partial unlinking, in the PDF, along with a description of the unsorted bin attack itself. Don't forget that the malloc testbed has a bunch of different bugs and can be linked against any version of GLIBC from 2.23 to 2.31, compiled with and without the tcache. It's a great way to learn about malloc internals and test your exploits, and honestly, I wish I had something like it when I was first learning about memory allocators. Join me in the next video, where we'll be taking on the first phase of the House of Orange, before finally putting all three phases together. In this video, we're going to cover Phase 1 of the House of Orange. This phase can sometimes be omitted if an appropriate bug is present, but I think it helps showcase the beauty of this technique. So we'll learn the full House of Orange as it was originally published. Since we're starting at Phase 1, we might as well get acquainted with our vulnerable binary. So navigate to the House of Orange directory, in which you'll find the House of Orange binary and matching pwntools template. Checksec reveals that the binary was compiled with full relrow, stack canaries, NX, and is position independent. It's also linked against GLIBC version 2.23, the earliest version of GLIBC we'll be dealing with during this course. So phase 1 depends, of course, on what sort of bug this binary has. So let's load it into GDB, run it, and find out what we're dealing with. There's both a libc and heap leak to allow us to focus on the technique, and we're presented with some slightly different options than normal. Option 1 allows us to request up to 2 so-called small chunks. And when we select that option, we're not prompted for a size. The binary has already chosen it for us. Breaking in GDB and inspecting the heap with viz shows that this binary is requesting hex 20 sized chunks every time we pick option 1. Now there's nothing special about 20 sized chunks, and we'll eventually see that these chunk sizes aren't very important at all. Option 1 works like this to streamline how we interact with the binary so we don't get too far off course when considering what to do next. Production binaries may give a user more or less control over the size and number of requests to malloc. Option 2 requests a single large chunk. Large in this case is also a relative term, but we can find out what the program considers a large chunk by breaking in GDB and this time issuing the heap command. Heap prints a summary of the default heap, although it can be used to print other heaps too, and it's great for getting an overview of a heap with large chunks on it, something that viz isn't well suited for. We can see from its output that after the 20 chunks, a hex FD0 sized chunk has been allocated, which is just short of a page on this architecture. Again, there's nothing special about this size of chunk, it's just large enough to trigger a specific malloc behavior that we'll be introduced to shortly. Lastly, option 3 allows us to edit specifically the first small chunk that we allocated, whether that was before or after the large chunk. I'll write some garbage data into it, then inspecting the heap shows us that that data was written into the first small chunk's user data. You'll notice there's no target option this time. Remember that the House of Orange is a technique designed to drop a shell, so that will be our aim throughout. At this point, I want you to pause the video, get familiar with the House of Orange binary, and see if you can find the bug. Once you've done that, return here and we'll start considering our options for exploiting this binary. If you found the bug, good work. If not, I can tell you that this binary has a heap overflow bug in the edit option. If I pick edit and send too much data for a 20 sized chunk to hold, when I break in GDB and inspect the heap with DQ and our MP trick, we can see that my data has overflowed from that first 20 chunk into the succeeding chunk. This overflow is pretty egregious, clocking in at 216 bytes. We could certainly argue over realism here, and different bugs might allow us to achieve the same result, but this bug simplifies things to help us learn the technique. So let's consider how we might leverage this heap overflow. The way I've used it here allows me to overwrite the size fields of the other 2 chunks on this heap. But that's not much use if we can't convince malloc to operate on them somehow once we've tampered with their size fields. And the only thing malloc can do to an allocated chunk is free it. Conspicuous by its absence in this program is a free option, which begs the question if phase 2 of the House of Orange is an Unsortedbin attack, which requires a free unsorted chunk, how are we going to leverage the unsorted bin attack if we're unable to free chunks in the first place? Well, that's what phase 1 is going to answer for us. We need to somehow leverage our overflow to generate a free chunk, using only calls to the malloc function. And we know overwriting other chunks' size fields won't help. Our only other option is the top chunk size field. In the house of force, we overwrote the top chunk size field with a large value. That's no use here because we're restricted to 3 comparably small chunks. But what would happen if we replaced it with a small value? To answer this, we need to understand what malloc does when it receives a request too large to be serviced from an arena's bins or top chunk. First, it will attempt to acquire enough memory to accommodate the request. Normal arenas achieve this by changing the permissions on pre-mapped heap memory, but the main arena does things differently. It invokes the break syscall to request more memory from the kernel. Malloc then uses the top chunk size field to determine whether the new memory is contiguous to the end of the heap. If it is, malloc simply extends the top chunk into the new memory and makes the allocation from the now larger top chunk. But let's consider what would happen if this occurred after we had overwritten the top chunk size field with a small value. When a large request arrives, malloc does the same as before, requesting more memory via the break syscall. But now it appears to malloc as though the new memory doesn't border the end of the heap. When this happens, malloc assumes that the kernel was unable to map contiguous memory for this heap. Perhaps it ran out of space. And since the new memory is larger, malloc starts a new heap there instead. It does this by setting the main arena's top chunk pointer to the new memory, and so as not to waste space, it frees the old top chunk. So if we leverage the overflow bug to shrink the top chunk, then make a request larger than the top chunk, malloc will generate a free chunk in the path of our overflow, which we can use for our unsorted bin attack, all without the process ever calling the free function. And this is phase 1 of the House of Orange. So now that we have a plan, let's make a copy of the template script and open it in our editor. Scrolling to the example shows us the 3 helper functions for this binary. Small malloc to request those 2 0-sized chunks, large malloc to request a chunk just short of a page size, and edit to write data into the first small chunk. Start by removing the call to large malloc. We'll keep the first small malloc call since that's the chunk we're going to overflow from, and the edit call which we'll use to trigger the overflow. The edit call already fills the first small chunk's user data, so anything we add after that will overflow into the top chunk size field. Let's set the top chunk to a 9-0 sized chunk. That way, when it's freed, it will get linked into the unsorted bin. Then confirm this worked by running our script with the debugging options. Let's switch to the binary to make the large request, which will trigger the top chunk extension code. Unfortunately, we encounter an error message. This one is actually the result of a failed assert rather than a malloc print error check. But the result is the same. The process stops. Switch back to GDB so we can reveal the source of this error. Use the frame command to switch to the sysmalloc frame. It's this function that's responsible for requesting memory from the kernel on malloc's behalf. The context code command shows us the assert statement that's causing problems. We're running afoul of these 2 lines specifically. The first checks whether the top chunk's prev-in-use flag is set. Since the top chunk should always have a set prev-in-use bit, it's an error to have it cleared. The second line is checking whether the top chunk ends on a page boundary, which it currently does not. So we need to return to our editor and make these changes. Let's start by setting the top chunk size field to a value that aligns the end of the top chunk to a page boundary. We can do this by subtracting the space we've already allocated, a hex 20 sized chunk, from the size of a page on this architecture. And don't forget, we also need to add 1 to set the prev in use bit. Those changes should satisfy the assert statement in sysmalloc. So now we can add a call to the large malloc helper function to trigger the top chunk extension code. Run your script with the debugging options, and this time the program continues to run. Break in GDB and invoke the heap command, which reveals that there's now a free unsorted chunk directly in the path of our overflow from that 20 chunk. For the curious, the viz command shows malloc's use of so-called fence post chunks. These are illegally sized hex 10 chunks, which are placed at the end of a heap that no longer has a top chunk. Their purpose is to allow malloc to safely look forward 2 chunks when determining forward consolidation candidates without accidentally reading unmapped memory. Now that phase 1 is complete, we're in a position to overwrite the old top chunk's BK, setting up our Unsortedbin attack. But how do we tie phases 2 and 3 together? What's the link between an Unsortedbin attack and file stream exploitation? Well, we learned about how vtable hijacking features in file stream exploits. So what if we targeted one of the standard I/O vtable pointers? Our Unsortedbin attack would replace that vtable pointer with the address of the main arena's unsorted bin. Then, the next time a standard I/O member function was called, the main arena would be treated as a vtable. This isn't particularly helpful. The main arena consists primarily of empty linked lists at this point, and attempting to execute those addresses would just lead to a general protection fault as we tried to execute memory marked as non-executable. Even if we were to populate some of those bins with pointers to heap memory by sorting chunks into them, heaps are no more executable than arenas. So what other options do we have? Well, what about the IOListAll pointer? Remember that IOListAll is the head of a list of every file stream this process has open, and it's used when GLIBC needs to perform an operation on all open file streams, typically cleanup procedures. One of those cleanup procedures is performed when a program exits, either via the GLIBC exit function or by returning from its main function. Let's say we target the IOListAll pointer with our Unsortedbin attack, replacing it with a pointer into the main arena. Then we exit the program. As the program exits and GLIBC cleans up, it will attempt to flush the buffers of any open file streams. It does this by iterating over every file stream in the IOListAll list, determining whether its buffers require flushing, and if so, calling a specific member function named Overflow on that file stream. Nothing to do with the sort of overflows we've been dealing with, mind you. This is a more interesting situation, because now the main arena is being treated as a file stream, and this gives us the opportunity to point one of that file stream's fields at heap memory that we control. We can do this by sorting the old top chunk into a bin of our choosing. We control its size field via the overflow bug, after all, and if we request a non-exact fitting chunk, it will get sorted rather than allocated. But our Unsortedbin attack will still work because, as we learned earlier, sorting still involves a partial unlink. Things are getting complicated, so let's return to our editor and make some changes so we can visualize what we're trying to achieve. We'll add a line that sets up our Unsortedbin attack against the IOListAll pointer. Using the edit helper function, we'll overflow a second time into the old top chunk, setting its size field to hex 21. We'll keep writing, setting the chunk's FD to any value and its BK to the address of IOListAll -16. By doing this, we've created a situation where there's a 20 sized chunk in the unsorted bin with a BK that points near the IOListAll pointer. Lastly, we'll add a call to the small malloc helper function to make a request for a 20 sized chunk. This will cause malloc to allocate the old top chunk since we set its size to hex 20, triggering our unsorted bin attack against IOListAll. I know I said we'd sort the old top chunk rather than allocate it, but let's take this one step at a time. Once you've added those lines, run your script with the debugging options. Break in GDB and print IOListAll to confirm that our unsorted bin attack was successful. We can see from the output that it now points into the main arena. Now, we're by no means done yet, but let's exit the program anyway and see what GLIBC makes of its new IOListAll pointer. Continue in GDB, switch to the program window and select the Quit option. Then switch back to your GDB window. The pwntools scripts for this technique set a breakpoint on the GLIBC function responsible for flushing file stream buffers during cleanup, and that's the breakpoint we've hit here. The backtrace panel shows us that this function is called IOFlushAll-LockP, and that it was called from IOCleanup. If we continue, the process unsurprisingly segfaults, and shown in the source panel is the check that IOFlushAll-LockP uses to determine whether a file stream requires flushing. The reason for the segfault is irrelevant. After all, this function is trying to treat the main arena like a file stream. What is important is how this check works. The line containing IO overflow in all caps is the one calling the overflow member function. The first argument, FP, represents the file stream overflow is being called from. There are two checks prior to this line, each one of which must pass in order for overflow to be called. The first check passes if the mode field of the file stream is less than or equal to 0, and its IOWrite pointer field is larger than its IOWrite base field. Essentially, this is checking if anything remains to be written in this file stream's buffer before the program exits. I'll leave the second check for you to decipher on your own, but note the test for mode larger than 0. If we dereference IOListAll with print, we can see things from the IOFlushAll-LockP function's perspective. The file stream that it thinks overlaps the main arena has a negative mode field, but its IOWrite base and pointer fields are identical, meaning it will fail the first check due to the latter and the second check due to the former. In this case, IOFlushAll-LockP won't call this file stream's overflow function, and will instead move on to the next stream via the current stream's chain pointer. We can see that right now, chain points back into the main arena, and with a little GDB foo, we can print the address of the chain member. If we combine this with DQ to dump 26 quad words of the main arena, we can determine which part of the main arena is being treated as the chain pointer. If the DQ output looks slightly odd, that's because earlier versions of GLIBC, like this one, 2.23, have one less quad word at the start of their arenas. You can take a look at the arena layout diagram in the PDF to find out which one. Nevertheless, using that diagram, we can determine that this is the top chunk pointer, making these the unsorted bin FD and BK respectively. And then we can just count the small bin BKs in increments of 16 bytes. 20, 30, 40, 50, 60. The BK of the 60 small bin is what's being treated as this rogue file stream's chain pointer. So if we change the size field of the old top chunk from hex 21 to 61 before our unsorted bin attack, the old top chunk will be sorted into the 60 small bin, rather than being allocated, and end up as the chain pointer of the rogue file stream overlapping the main arena. This allows us to forge our own fake file stream on the heap, providing our own vtable pointer and vtable entries. Sound complicated? Don't worry, the House of Orange is one of the more involved heap exploitation techniques, so don't hesitate to rewind the video and revisit the material until you're comfortable with it. Once you are, let's continue. Download the second House of Orange template script from this lecture's resources, the contents of which are on my screen now. We're going to use this to avoid too much typing. This technique is difficult enough as it is. The first part of this script does exactly what we did earlier. Leverage a heap overflow bug to shrink the top chunk, then make a request that it couldn't service to generate a free unsorted chunk in the path of our overflow. The second part uses the overflow again to set up both our Unsortedbin attack and forge a counterfeit file stream on the heap. Remember that you can use the ptype or dt commands in pwndbg to find out the offsets of each field when you're building structs like this. Notice that the old top chunk's size is being set to hex 61 to ensure it gets sorted into the 60 small bin, and its bk is being overwritten with the address of IOListAll -16, the target of our Unsortedbin attack. The remaining fields belong to the file stream overlapping the old top chunk that we'll finish crafting now. When our exploit triggers the IOFlushAllLockP function, it will follow the corrupt IOListAll pointer to the main arena, which will fail the buffer flushing checks. It will then move on to the next file stream by following the chain pointer, which overlaps the 60 small bin bk. The old top chunk will have been sorted into this position during the Unsortedbin attack, so IOFlushAllLockP will follow the chain pointer to the heap where our fake file stream resides, perform the buffer flushing checks on it, and hopefully call its overflow member function. All we have to do is ensure that our counterfeit file stream passes those buffer flushing checks and provide a vtable pointer to a vtable in which the overflow entry is populated by the function we want to execute. If you remember the buffer flushing checks, then pause the video briefly and modify the write base, write pointer, and mode variables to ensure they pass. If not, then just follow along with me now. The write base field must be less than the write pointer field, so let's set them to 1 and 2 respectively. The mode field must be less than or equal to 0, so let's set it to 0. Now the buffer flushing checks will pass, and the overflow entry in this file stream's vtable will be called. The vtable pointer is already set up. It just needs to be a pointer to controlled memory. In this case, I've saved a little space by overlapping the fake vtable with an unused part of our file stream, but it could theoretically be placed anywhere. The contents of the overflow variable will form the overflow entry in our fake vtable. Before we try to use a OneGadget here, recall that when the overflow function is called, its first argument is the address of the file stream it's called from. That means if we write the string bin sh into the first quad word of our file stream, which is where the flags field resides, then point the overflow vtable entry at the GLIBC system function, the call becomes system bin sh, and we'll get a shell without the need for a OneGadget. And all of this sounds great, but there's just one problem. Remember, when we practiced the Unsortedbin attack, we made sure that the corrupt chunk was allocated rather than sorted. This was because the partial unlink has the side effect of copying our corrupt bk over the Unsortedbin bk, meaning that if the corrupt chunk is sorted, malloc will continue searching the unsorted bin, following the corrupt bk, and inevitably failing the unsorted bin's size sanity check at the destination. This would result in one of the dreaded malloc print error calls, aborting the process. Nonetheless, let's run our script with the debugging options to confirm that everything is in place, and we can address that issue shortly. GDB stops, And looking at the backtrace panel, we see the familiar pattern of malloc print error followed by abort. But look at the current frame. We've actually stopped in IO flush all lock P, the exact function we wanted to trigger. It turns out that in GLIBC versions prior to 2.27, the abort function flushes file streams, because what's more sensible than operating on data after detecting corrupt data? We know what IO flush all lock P is going to do, so let's follow the chain. Dereferencing IO list all shows us what we saw earlier, a file stream overlapping the main arena that fails the buffer flushing checks. This time, however, the chain member points to the heap rather than back into the main arena. We can use some GDB foo to follow the chain pointer and see what will be made of our counterfeit file stream. Note our IO write base and pointer fields set to 1 and 2 respectively, a mode field of 0, and an overflow vtable entry of system. Lastly, the flags field at the start of the struct contains the string bin sh. Let GDB continue, and even though it will complain at us, if we switch to the program window, we've snatched a shell from the jaws of abort. Notice how GLIBC had even got as far as printing an error message and a backtrace before the shell dropped. Not bad for just 3 calls to malloc. And that is the House of Orange. To summarize, we leveraged an overflow into the top chunk to shrink its size field to a small page-aligned value. Then we made a request too large to be serviced from the newly shrunken top chunk. This triggered malloc's top chunk extension code, which requests memory from the kernel, and if that memory is contiguous to the top chunk, extends the top chunk into it. However, because we had tampered with the top chunk size field, from malloc's point of view, the newly acquired memory wasn't contiguous to the top chunk, so it was instead used as the new top chunk, whilst the old top chunk was freed into the unsorted bin. This left us with an unsorted chunk in the path of our overflow. We leveraged the overflow a second time to overwrite the unsorted chunk's backward pointer, setting up an Unsortedbin attack against the IO list all pointer. We also took this opportunity to forge a file stream on the heap, overlapping the old top chunk, and set the size of the old top chunk to hex 60. Then we made a third and final request for a chunk that wasn't 60 sized. Malloc, finding neither fast nor small chunks to service our request, began searching the unsorted bin, where it came across the old top chunk. But it wasn't an exact fit, so malloc sorted it into the 60 small bin, triggering our unsorted bin attack in the process. Malloc continued to search the unsorted bin, following a now corrupt BK to a non-existent chunk, which failed a size sanity check, causing GLIBC to begin its abort procedure. Before sending our process the abort signal, GLIBC attempted to clean up its open file streams. It began by following the corrupt IO list all pointer to the main arena, the pointer having been subject to our unsorted bin attack and now holding the address of the main arena's unsorted bin. When treated as a file stream, the main arena failed the checks that would trigger a call to its overflow function, causing the cleanup function, IO flush all lock P, to move on to the next file stream in the list via its chain pointer. The chain pointer overlapped the 60 small bins BK, which was where the call to malloc that started this whole series of events sorted the old top chunk, and where our fake file stream resided. We had crafted our fake file stream such that it would pass the checks in order to have its overflow member function called, at which point our vtable pointer was followed to our fake vtable, in which we'd replaced the overflow entry with the address of the system function. The overflow function is normally called with a pointer to its file stream as the first argument, and we'd replaced the flags field of our file stream with the string bin sh. This resulted in the call to overflow being interpreted as a call to system bin sh, dropping a shell and bringing us to the end of the House of Orange technique. Now, I know that was a lot to take on board. We've learned new malloc internals, we learned about the Unsortedbin attack, and a little bit about file stream exploitation. So don't feel pressured to move on to the next video until you're comfortable with this technique. There's one last challenge binary you're going to face, and you'll need to have a solid understanding of the House of Orange to tackle it. So review this video, consult the PDF for a summary of the technique and a recap of the malloc internals involved, and as usual, there's a commented solution script available from this lecture's resources. But before we wrap this video up, there's a few important things to note about the House of Orange. The first is that Phase 1 can be ignored entirely if you're able to tamper with existing unsorted bin metadata. We had to leverage the top chunk extension code because our vulnerable binary wouldn't allow us to free chunks, and there were none present as part of normal operation. This might not be the case in a production binary, which is much more likely to have free chunks available. Also related to Phase 1 is the fact that the top chunk extension code we took advantage of only works like that when the arena in question is the main arena. Other arenas aren't vulnerable to Phase 1 as their top chunk size isn't used to determine whether newly acquired memory is contiguous. Lastly, and most importantly, notice that for the first time, our exploit isn't 100% reliable when run under production conditions. Sometimes we get a shell, other times we don't. The reason behind this lies in how the mode field of the rogue file stream that overlaps the arena is formed. Mode is a 32-bit field, and ends up overlapping the least significant bytes of the C0 small bin FD. This results in its most significant bit, the one that determines whether it's interpreted as a negative value or not, being subject to ASLR. If we run our exploit with GDB attached, but without ASLR disabled, continue at the IOFlushAllLockP breakpoint, and wait for the process to segfault instead of dropping a shell, we can see that the file stream overlapping the main arena passed the buffer flushing checks this time, and IOFlushAllLockP attempted to call its overflow function, resulting in a segfault. Printing the FP variable now confirms the fault occurred whilst processing the file stream overlapping the main arena, and that its mode field was interpreted as a positive value this time, dropping through to this second buffer flushing check, which it passed. The reason it passes that second check is left for you to pursue, but it's possible to counteract this behavior by sorting chunks into different bins before you finalize your attack. We just didn't have the heap control to do that here. The reason we targeted the chain pointer rather than the vtable pointer of the file stream overlapping the main arena is also left as a research project. Once you're happy with the House of Orange and its limitations, we're going to cover one more malloc internals concept, remaindering, before we tackle the last challenge binary to test what you've learned. I'll see you in the next video.
The next challenge binary is difficult, and we'll need to learn one more piece of malloc internals, remaindering.
Remaindering is simply the term the malloc maintainers give to splitting one free chunk down into two, then allocating one of those parts whilst the other part is returned to the free lists. The how of remaindering is relatively simple. Say we've requested a hex 100 sized chunk, but our arena only has a 300 chunk to give us. Malloc will unlink the 300 chunk from its free list, split a 100 chunk off of it, link the so-called remainder into the head of the unsorted bin, and allocate the 100 chunk. The when is more complicated. Remaindering can occur at one of 3 points in the malloc flowchart. It happens during allocations from the large bins, which aren't covered in part 1 of this course, and during something called a bin map search. You can see from the malloc flowchart in your PDF that a bin map search is one of the last allocation paths before the top chunk is used. Binmap is a play on the word bitmap, and it's quite literally a bitmap representing which of an arena's bins may be occupied. I say may because it's a lazy bitmap, meaning that a bit is only cleared when malloc attempts to allocate from an empty bin during a binmap search. The binmap itself resides towards the tail end of an arena, as you can see from the arena layout diagram. A binmap search works like this. Malloc uses the binmap to find the next largest occupied bin with respect to the requested chunk size. Then it remainders the last chunk in that bin. When a chunk isn't large enough to be remaindered by a request and leave behind at least a minimum sized chunk, this leads to so-called exhausting. If you requested an 8.0 sized chunk, but the arena only had a 9.0 chunk, malloc would exhaust that chunk and you'd be allocated the whole 9.0 chunk. This is one of the few times you won't get the exact chunk size you expected. This brings us to the third point at which remaindering can occur. If a chunk was remaindered during a binmap search and the request size was within small bin range, the arena's last remainder field is set. You can see the last remainder field in your arena layout diagram between the top chunk and the unsorted bin FD. The last remainder field is just a pointer to the last chunk to get remaindered. And the last remainder field works in conjunction with the unsorted bin. During an unsorted bin search for a small chunk, if the search gets to the last chunk in the unsorted bin, and that chunk is also the last remainder, then that chunk will be remaindered again, and the last remainder field will be updated accordingly. Oddly, chunks aren't exhausted from the last remainder, although you'll still witness the same outcome as the chunk is sorted and then exhausted via the subsequent binmap search. Let's briefly visit the malloc testbed once again to see remaindering in action. Make another copy of the pwntools template and open it in your editor. Keep the lines that request chunks A and B and the line that frees chunk A. Discard the rest. Change chunk A's size to hex 1F8, which will yield a 200 sized chunk. Remember, you can just subtract 8 from your desired chunk size to get an appropriate request size for that chunk. Run your script with both the usual debugging options, break, and inspect the heap with viz, the output of which shows that we have a 200 sized unsorted chunk on our heap. Continue and switch to the program window, where we'll use a request size of F8 to allocate a 100 sized chunk. Return to GDB and break again, at which point viz shows us that the 200 sized chunk has been split in half, or remaindered, to service our request. The lower half, in terms of address, became the hex 100 sized chunk that we wanted, whilst the upper half has been linked back into the unsorted bin, becoming the last remainder in the process. Although it appears as though the 200 chunk was remaindered directly from the unsorted bin, this isn't actually the case. It was first sorted into the 200 small bin, then remaindered from there via a binmap search. If we were to make a request for, say, an 8.0 sized chunk now, then the 100 chunk would be remaindered directly from the unsorted bin because it's the last remainder. Regardless, the final result is the same, and while remaindering isn't a complicated procedure, there's a lot to remember in terms of when it can happen. So, for the purpose of the next challenge binary, we can think of remaindering simply as malloc will split apart free chunks to service a request if it can't find an exact fit. If you want to refresh your memory on remaindering, there's a remaindering section in your HeapLAB PDF, and I would also suggest using the malloc testbed to follow the remaindering process. Don't forget that each version of GLIBC in the course material is packaged with its malloc source code, which means if you set a breakpoint on the malloc function, you can trace through the source and identify the path through malloc your requests are taking. Once you're comfortable with the basics of remaindering, you're ready to take on the final challenge binary. So I'll see you in the next video.
It's time for another challenge binary. This one is called One-Byte, and it's difficult, so take your time with it and work through at your own pace.
As I said before, it's completely acceptable for it to take hours, if not days, for you to build a working exploit on your own. We'll approach this challenge in the same way we did the last challenge binary. I'll work with you through the characterization phase, where we find out what sort of control we have over our program. Then I'll leave you to find the bug and develop an exploit. The goal here is the same as before. Drop a shell from the challenge binary by leveraging its heap-related bug. Start by navigating to the challenge-1byte directory, where we see the challenge binary itself along with its pwntools template script. Let's start with our usual drills, discovering the binary's security stance with checksec. It looks like this challenge was compiled with the full suite of protections, including full railrow, stack canaries, NX, and position independence. It's linked against GLIBC version 2.23, which hopefully gives you a hint as to which technique you might want to leverage. Load the binary into GDB and run it. The first thing you'll notice is that this program does not leak the address of any of its components. Not the binary, nor the heap, nor its libc load address. Until now, our vulnerable binaries have kindly leaked their libc and sometimes heap addresses for us, so that we could concentrate on learning the different techniques. Of course, in a production environment, that's highly unlikely. Exploit development against modern systems often requires some form of information leak. And in this challenge, it's up to you to forge that info leak. The numbered menu is still here. Option 1 allows us to request up to 16 chunks, which is generous by our standards, bearing in mind we just dropped a shell with no less than 3. But we don't get a say in how large these chunks are. Breaking in GDB and inspecting the heap reveals that the challenge binary is requesting hex 60 sized chunks when we use option 1. Option 2 allows us to free chunks by index, starting at 0. Option 3 lets us edit a chunk's contents once it's been allocated. And with option 4, we can read back the contents of an allocated chunk. So, in summary, we can request up to 16 60-sized chunks, free them, and read and write to their user data. But there's one way in which this binary is subtly different to the others we've come across. We can use the ltrace program to trace which library calls the One-Byte challenge is making at runtime. By default, the output can get a little messy, so we'll use a search filter to trace only functions that end in alloc. The PDF documents malloc's core functions, a couple of which are wrappers around malloc that provide extra functionality. Selecting option 1 from the menu with ltrace attached reveals that the One-Byte challenge is using the calloc function to request memory, rather than malloc. As the PDF states, calloc uses malloc to make memory requests, then ensures that memory is zeroed before returning it to the caller. The challenge binary makes all its requests via calloc to simulate how a programmer might properly initialize their variables before use. So if you thought you could leak malloc metadata by freeing a chunk, then allocating it again and reading from it, you're out of luck. I'll briefly demonstrate the effect calloc has on the heap by first requesting a chunk, filling it with garbage data, then freeing it. Inspecting the heap at this point shows a free 60-sized chunk, the first quad word of which has of course been overwritten by a null fastbin fd, indicating the end of the 60 fastbin. but otherwise my data is intact. If I return to the binary, request another 6.0 chunk, break, and inspect the heap once more, now all of my data, including any malloc metadata that might have been there, has been zeroed. So, fixed chunk sizes and zeroed memory, this certainly won't be easy. Start by finding the bug. There's one in there somewhere. Once you've done that, concentrate on leaking a libc address. Because you know which version of glibc is in use, you can subtract the offset of whichever part of libc you leak from its runtime address, giving you the libc load address. Setting libc.address to a specific value in your pwntools script will automatically update future calls to libc.sim, allowing you to continue as normal once you've leaked its base address. And the template script contains an example of how you might do this. Don't forget you've got lots of resources to hand, including the HeapLAB PDF and the malloc testbed. When the prompt appears, pause the video and see how much damage you can do on your own. If you get really stuck or just want to check your work, go ahead and resume this video and I'll point out the bug. Did you find the bug? If not, let's try a few things and see if we can trigger any unusual behavior. Load the binary into GDB and run it. The first thing we'll check for is a double free. We can do this simply by requesting a chunk, then attempting to free it twice in a row. No double free bug. Okay, how about a use after free? We may be able to write to or read from a chunk's user data after it's been freed, allowing us to tamper with or leak malloc metadata. But alas, it looks like this program correctly deals with free chunks. And we know we can't simply allocate a free chunk, then read its vestigial malloc metadata, because calloc will zero it again before we get a chance. Then how about an old-fashioned overflow? I'll request that first chunk back from the Fastbins and request a second chunk following it. Then I'll edit the first chunk and attempt to write more than 88 bytes into its user data, 88 bytes being the amount of user data for a 6.0 sized chunk. Breaking in GDB and inspecting the heap reveals that this program indeed has a single byte overflow bug. Where the second 6.0 size field should be is now a hex 59 or capital Y character, which has confused the viz command somewhat. Now that we've found the bug, we need to consider what sort of control a single byte overflow gives us. Not a huge amount, certainly. 1 byte wouldn't make much of a difference to the top chunk size, for example. But as we've seen, overwriting a 6.0 chunk size field changes its size completely. This could allow us, for example, to change a chunk's size field, then free it, potentially freeing space that overlaps other allocated chunks. Now's the time to start thinking about how you might leak libc and perhaps the heap as well. It's possible to leak both via heap corruption. Ignore the top chunk and focus on changing chunk sizes using the overflow. Remember that the program's read option lets you read data from the heap and that we didn't cover remaindering for nothing. Consider how you might coerce a libc address onto the heap. After all, 6.0 chunks will be linked into the Fastbins when freed, which only use heap addresses in their forward pointers. The pwntools template for this challenge contains some useful comments on what to do with your libc leak once you've obtained it. Pause the video again and see what progress you can make on your own. Return here if you need a hint. Welcome back. I've made some changes to the template script, and you can download the copy we're looking at from this lecture's resources. It's labelled as Template 2. My intention is to show one way we could coerce a libc address onto the heap. I've started by requesting 4 chunks, A through D. Then I've edited chunk A, leveraging the single byte overflow to overwrite the least significant byte of chunk B's size field, using a C1 value. Note the use of the P8 function here to write a single byte. The reason I picked a C0 size is because it's the sum of 2 6-0 chunks, meaning everything on the heap still lines up and we're less likely to trigger any seg faults or mitigations. Next, I've freed chunk B, which will be treated as a C0 sized chunk and linked into the unsorted bin. I'll run my script with the GDB and no ASLR options, break with Ctrl-C, and inspect the heap with the viz command to see what effect this has had. We see chunk A, full of garbage data, followed by chunk B, which appears to be a free C0 sized chunk, linked into the unsorted bin. Chunk D borders the top chunk and has a clear prev in use bit, along with a prev size field that matches chunk B's size. So our actions resulted in linking chunk B into the unsorted bin, which it otherwise couldn't have been, a side effect of which is that libc addresses in the form of this pair of unsorted bin links were written to the heap. Unfortunately, we can't read this specific pair because the program won't let us read from free chunks. But don't forget about chunk C. It's still there and it's still allocated, meaning we can read from and write to it. Have a think about how we might use remaindering to our advantage here, not only to leak a libc address, but to set up a metadata overwrite as well. Pause the video and come back if you need help crafting the libc leak. I've added more lines to the last template. You can grab a copy of this one from the resources section as well. It's number 3. The only change I've made to the heap is request another 6-0 sized chunk, which I've labelled chunk B again, since it takes the same spot on the heap. This causes malloc to perform the following actions. Search the fast bins and small bins for a 6-0 chunk, and failing that, search the unsorted bin for a 6-0 chunk. On finding the C0 chunk in the unsorted bin, sort it into the C0 small bin. Fall back to a bin map search and remainder the C0 chunk, allocating the first part to the program and linking the remainder back into the unsorted bin. At this point, the remainder from that operation neatly overlaps chunk C, and the first 2 quad words of chunk C's user data have been overwritten with unsorted bin forward and backward pointers. This is our opportunity to read from the still allocated chunk C, leaking the address of the main arena's unsorted bin. And that's all the rest of the script does. First, we have to use the read helper function to read the contents of chunk C. The read helper just returns all 88 bytes the program gives it in string format. So the next line uses the Python slice syntax to isolate just the first quad word of that data, then unpacks it into an integer with the pwntools use64 function. You can read more about the pwntools unpacking functions from the PDF and the pwntools online documentation. Now we've leaked the address of the main arena's unsorted bin, and we can calculate the libc base address from it. All we need to do is take the offset of the unsorted bin from the start of the libc shared object and subtract it from the unsorted bin's actual address. Arenas don't actually have an unsorted bin member. The closest we can get with pwntools is the main arena symbol. In this case, the unsorted bin is hex 5 8 bytes after the start of the main arena, so we just hardcode that value. Note that you can add your own symbols to ELF objects for pwntools to use if you want, rather than using variables like I've done. This line does the aforementioned calculation and sets libc.address with the result. This updates all the symbols in the libc object, so now we can use things like libc.sim.system, just like we did against the other vulnerable binaries. The last line just logs the libc address, so we can cross-reference with GDB to confirm all this was successful. I'll run my script with the debugging options and take a look at the heap. It's almost repaired back to its original state with 4 6.0 sized chunks. The only difference is now there's a free 6.0 chunk in the unsorted bin overlapping chunk C. If I switch to the program window, we can see the output of that logging function, claiming that libc was loaded at this address. Switching back to GDB and using the vmmap command confirmed that this process's copy of libc was indeed loaded at that address. So now that you're able to leak libc, you can target libc data structures in the next phase of your exploit. It's also worth considering whether you need a heap leak to achieve your goal, because it would be easier to do that now whilst the heap is stable. And don't forget that now you've created overlapping chunks on this heap, you can not only read malloc metadata, but overwrite it too. This is a great example of how one type of heap bug can be turned into different primitives. For example, we started out with a single byte overflow, but now we essentially have a use after free, and could even leverage this situation to coerce a double free. I'll leave you to plan the next phase, so pause the video again and come back if you need a steer towards a specific technique. We had a lot of options before the pause, so let's pare them down to find a sensible choice. I mentioned we could leverage our situation for a double free. That could be done by, for example, requesting the remainder overlapping chunk C, then immediately freeing it into the Fastbins. Next, free a different chunk to bypass the Fastbins double free mitigation, then free chunk C again. I'm not sure the Fastbin Dup route is the best, however. We can't request 7.0 sized chunks, and even though we were able to deal with that restriction in the previous challenge, here we're constrained to requesting only a single chunk size, making this approach difficult, if not impossible. We could set up the safe unlink technique, since we're able to clear prev in use flags. But since we're unable to leak the binary or the stack, where this program stores pointers to its heap memory, it would be tough to capitalize upon. Then what about the House of Orange? We know we can tamper with unsorted bin metadata at this point via chunk C, which overlaps the remainder in the unsorted bin. And now that we've leaked libc, we could target the IOListAll pointer with an unsorted bin attack. We control enough data on the heap to craft a fake file stream and vtable, and all we'd need to know is the address of our fake vtable to put in our file stream's vtable pointer. This means we're going to need a heap leak. At this juncture, you can choose to proceed with the House of Orange, or pick your own technique. Either way, pause the video and see what progress you can make towards your technique of choice. Head back here if you need some advice on leaking the heap. I'm going to proceed with the House of Orange technique, which we'd decided we need a heap leak for. And I've added some lines to my exploit script that will do just that. You can download this template, which is number 4, from this lecture's resources. Notice that I've rewritten the libc leak as a single line. It's less readable, but we know what it does by now. My plan here is to write more malloc metadata into chunk C, this time a heap address, and leak it the same way we leaked the main arena's unsorted bin. If you took a different approach to leaking libc than I did, The next part may be easier or harder depending on how you went about it. For example, if you were able to link a second chunk into the unsorted bin, then the remainder overlapping chunk C would have both an unsorted bin and heap address in it by now, which you could leak simultaneously. I'll continue from where we left off, having leaked libc separately. I've started by requesting the unsorted chunk, the remainder, overlapping chunk C. I've called this chunk C2. If I free chunk C2 now, it will be linked into the 6.0 Fastbin. But since it'll be the first chunk in that bin, its FD will be null. Instead, I free a different 6.0 chunk, I've chosen chunk A, then free chunk C2. Now chunk C2 has an FD that points to chunk A, which we can subsequently leak through the underlying chunk C, which is still allocated. I've used the same combination of read, slice, and use64 to perform the leak, the result of which I've saved in a variable named heap. No math is required this time because we're leaking the address of chunk A, which sits right at the start of the heap. The last line simply logs the leaked heap address so we can cross-reference with GDB. I'll check if this works by running my script with the debugging options. I'll break in GDB and issue the viz command. We see that, as expected, chunk A has been linked into the 6.0 Fastbin, with chunk C2 at the head of the same Fastbin, its FD pointing to chunk A. Of course, chunk C is still present, occupying the same space as C2. And if we note the heap start address, then switch to the program window, we can confirm that we've successfully leaked the heap. Now you've got all the information you need to leverage the House of Orange against this challenge binary. You can target the IO_list_all pointer with an Unsortedbin attack, courtesy of your libc leak, and you can forge a file stream on the heap, complete with vtable and vtable pointer, thanks to your heap leak. If you're following along with these templates, the next thing you'll need to do is return the heap to a state from which you can tamper with unsortedbin metadata again. Pause the video and attempt the remaining exploit steps on your own, starting with the Unsortedbin attack. If you're struggling to return the heap to its previous state, come back and I can assist. Now that we're ready to craft our House of Orange, we need to set up an Unsortedbin attack. We were in a position to do this before our heap leak, so we need to return the heap to that state. Again, depending on whether you followed the same pattern of allocations as me, you may need to take a different approach at this point. I've added some more lines to my script. All they do is overlap an unsorted chunk with chunk C, so we can tamper with unsortedbin metadata. You can download a copy of this template, which is number 5, from this section's resources. The first thing I've done is allocate chunks C2 and A back from the Fastbins. This returns the heap to its early configuration with 4 allocated 6.0 sized chunks. Then I've leveraged the overflow bug in the same way as we did before to overwrite chunk B's size field with a hex C1 value. I've freed chunk B into the unsorted bin, and lastly I've remaindered chunk B, leaving its remainder linked into the unsorted bin and overlapping chunk C, which is still allocated. I'll run my script with the debugging options, break in GDB, and inspect the heap with viz to assess the damage. As expected, there's an unsorted chunk in the exact same location that chunk C resides in. To prepare your unsortedbin attack, all that's required is to edit chunk C and overwrite the unsorted chunk's BK. To complete our House of Orange, we need to target the IO_list_all pointer with our unsortedbin attack. We must ensure that the unsorted chunk is 6.0 sized, which it already is in my case. That way it will get sorted into the 6.0 small bin when we make our final request. Lastly, we need to forge a fake file stream overlapping the unsorted chunk, ensuring that it passes the buffer flushing checks, and that it has a vtable pointer to a fake vtable. This will undoubtedly span more than one chunk, so you can use the dt command to remind yourself of each field's offset. You can also use some gdb foo to cast an arbitrary address to a file stream to check your values line up. Remember that your vtable's overflow entry must point to the system function, and the flags field of your file stream holds the command you want to pass to system. You may also need to request more chunks at the start of your exploit script to make room for your file stream. Now's the time to pause the video again and set about crafting your counterfeit file stream on the heap and setting up your Unsortedbin attack. If you're having trouble lining everything up, head back here and I'll help out. I've gone ahead and added the necessary lines to my script to set up both an Unsortedbin attack and a fake file stream on the heap. You can download this template from this lecture's resources. It's number 6. I needed to request one more chunk at the start of my script, which I've labelled chunk E, to make room for the file stream's vtable pointer. I've also used the edit helper function to write the string bin sh into the last quad word of chunk B, which forms the flags field of my file stream. I've edited chunk C, which occupies the same space as the unsorted chunk we generated earlier, to overwrite the unsorted chunk's bk, replacing it with the address of IOListAll -16. In the same edit, I've also set the IOWrite base and IOWrite pointer fields of my file stream such that they pass the buffer flushing checks. The mode field is already taken care of thanks to malloc zeroing the memory it occupies. Lastly, I've written my file stream's vtable pointer into the newly requested chunk E and pointed it back into the file stream where I've stored the overflow entry of my vtable, a pointer to system, in its unused to field. All of that should be enough to get us a shell when the next call to malloc is triggered. Recall that when we make that final request, malloc will search the unsorted bin, hopefully sorting the chunk with the corrupt bk into the 60 small bin, triggering our unsorted bin attack against IOListAll. Malloc should then abort when the next chunk in the unsorted bin fails the size sanity check, which in turn results in a cleanup operation that follows our corrupt IOListAll pointer to the main arena. The main arena hopefully fails the buffer flushing checks, and its chain pointer, which overlaps the 60 small bin bk, will be followed to our fake file stream on the heap. That should pass the buffer flushing checks, after which a call will be made into our fake vtable and result in tea and shells all round. I'll run my script with the debug options just to make sure that, if there are any snags, we can do a post-mortem. I'll break and use viz to check out the heap, where my fake file stream resides. I can use the gdb foo I showed you earlier to see what my fake file stream looks like. The IOWrite base and pointer fields look in order, as does the mode field. The flags field holds the string bin sh, and following my vtable pointer shows that the overflow entry in its vtable correctly points to system. If I invoke the Unsortedbin command, then print the address of the IOListAll pointer, we can see that my Unsortedbin attack is lined up correctly too. Everything is in place for our House of Orange. All that's left to do is make that last request to malloc to kick off the whole series of events. But the program keeps running. Returning to GDB shows neither a breakpoint nor segfault, nor the usual messy output when we get a shell. This is the final twist of the challenge, and I want you to think hard about why we didn't get our shell. Find out which parts of our attack worked and which didn't. be aware that after an unsorted bin attack, pwndbg can get confused over whether a chunk is linked into the unsorted bin or not, so don't take the output of its commands at face value. Pause the video and spend some time trying to fix this. Once you have, or if you're really stuck, come back and we'll find out what's going on together in the last part of this video. Did you figure out what was happening? It all comes down to the size of chunks we're able to request. When we made that final call to malloc, we were expecting our 6.0 chunk to get sorted into the 6.0 small bin. That's critical because it's the 6.0 small bin's BK that forms the chain pointer we want the IOFlushAllLockP function to follow. But in this challenge, we can only request 6.0 sized chunks. So when we made that last call to malloc, it allocated our 6.0 chunk rather than sorting it. Because it was still partially unlinked, our unsorted bin attack went ahead anyway, but because malloc found a chunk to allocate, it stopped searching the unsorted bin, and the call to abort never happened. That's why the program continued to function. If we quit the program now, or triggered a mitigation by requesting another chunk, for example, IOFlushAllLockP would still be called. However, because our 6.0 chunk never made it into the small bins, the chain pointer belonging to the file stream overlapping the main arena just points back into the main arena, and our fake file stream will never be processed. So how do we overcome this? We can't change our request size. The program only lets us request 6.0 sized chunks. And although in a production environment you may be able to trigger different sized requests by reading or writing to file streams or starting new threads, etc., this binary was designed not to give us that control. So, can we change the size of the chunk that needs sorting? Of course, if we do that, it will get sorted into a different bin. But let's consider for a moment what happens if the 6.0 small bin is empty when IOFlushAllLockP fires. When doubly linked bins are empty, their FD and BK both point to the bin itself. So when the chain pointer is followed, the next file stream to be processed will also overlap the main arena, just at a different offset. And if the bin overlapping that file stream's chain pointer is empty, the cycle continues. This gives us the opportunity to intercept the buffer flushing process by populating any of the bins that become chain pointers. I've added the final call to malloc to my script. If you haven't already, you can add it now or download this template from this lecture's resources. I'll run my script with the usual debugging options and break in GDB. This puts us back where we were before the last pause. Our unsorted bin attack has fired, but the process is still running. I'll use print to follow the chain pointer of the rogue file stream overlapping the main arena, the one that sits on top of the 6.0 small bin BK. We can see from the output that, as expected, it also resides in the main arena. So let's find out which bin this file stream's chain pointer overlaps. The pointer itself is at this address. And if we dump 36 quad words of the main arena, we can reference our arena layout diagram in the PDF to just count the bins until we find the right one. We see the top chunk pointer followed by the last remainder, then the unsorted bin BK, then the small bins start, 20, 30, etc., until we reach the matching address, which is that of the B0 small bin BK. So let's return to our exploit script and try to sort the chunk holding our counterfeit file stream into the B0 small bin rather than the 6.0 small bin. We only need to make a small addition. To the line in which we write the bin sh string into the flags field of our file stream, append a single byte. This byte will overflow into the unsorted chunk's size field, allowing us to set it to hex B1. Now when we run our exploit, the unsorted chunk won't be allocated, but this time sorted into the B0 small bin. Once abort has been triggered, IO flush all lock P will follow the corrupt IO list all pointer to the main arena, where it will process not one, but two file streams before following the second file stream's chain pointer to our bogus file stream on the heap. And we know exactly what happens after that, so let's run our exploit and see if we were successful. GDB makes its usual complaints when we drop a shell. That bodes well. And if I switch to the program window, we see that we did indeed finally get our shell. Of course, this exploit is no more reliable than your average House of Orange. If we run it under production conditions, we see about a 50% success rate on average. Before we wrap things up, there is an alternate solution to our chunk sorting problem, and I think it's a little more elegant. Close your editor for a moment and load the challenge binary into GDB. Ensure GLIBC is loaded by invoking the start command, then dump a portion of the malloc source code by typing the following. This code snippet is part of the Unsortedbin search process, and as the comment suggests, the first if statement decides whether a chunk is an exact fit for the current request. We know that exact fitting chunks are allocated from the unsorted bin, otherwise they're sorted into the appropriate small or large bin. This is the code responsible for allocating rather than sorting our 6.0 chunk earlier when our exploit was failing. The NB variable here represents the normalized request size. It's the result of malloc rounding up your request to the nearest actual chunk size. For example, if we had requested 3 bytes, NB would hold the value hex 20. In the case of our challenge binary, NB is always 6.0. The size variable represents the size of the unsorted chunk currently under inspection. Malloc masks off the chunk's flags prior to this comparison to stop them from interfering. But chunk size fields only hold 3 flags. The fourth least significant bit is neither a flag nor does it contribute to a chunk's size. During unsorted bin searches, it is not masked off prior to this comparison because there's no good reason for it to ever be set in the first place. So if we set the fourth least significant bit of our 6.0 chunk, giving it a size field of hex 6.8 or 6.9 if you want to keep the prev in use flag, it won't be considered an exact fit during requests for 6.0 sized chunks. Furthermore, the code responsible for sorting chunks into their respective bins does mask off. Specifically, it rotates away the entire low-order nibble of their size field, meaning that our chunk with the 6.8 size field will still be correctly sorted into the 6.0 small bin. So let's return to our editor one last time and find out if this alternate tactic works. Simply replace the B1 size field we wrote via the overflow with hex 6.8. You can actually use any value from hex 6.8 through 6f if you want. Normally that could cause heap stability issues later, but since this is the final stage of our exploit, it's not a concern. Running the exploit under production conditions, without any of the debugging options, eventually yields a shell. And that's it for the One-Byte challenge. You've successfully exploited a single byte overflow on the heap to get a shell. Not only that, the binary in question was compiled with modern protections, and you had to craft both a heap leak and a libc leak, whilst only being able to request a limited number of a single, and it turns out awkward, chunk size. On top of all that, our heap memory was being zeroed on allocation by the calloc function. So congratulations on beating that challenge. Even if you did need a steer through some of the more difficult parts, hopefully you've learned a lot. And if you want to review a working exploit, you can add that final change to the last template or download a commented solution script from this lecture's resources. That's it for learning material and challenges. Join me in the final video where we'll part ways.
Thank you for taking the HeapLAB Part 1 course. I hope that you enjoyed it and that you learned something.
We've seen that heap implementations can suffer from a variety of bug classes, not just overflows, but double freeze and use after freeze too. And even subtle bugs like a single byte overflow can lead to code execution. Don't hesitate to get out there and start searching for heap-related bugs. They can manifest in unexpected ways. For example, the realloc function that we haven't covered in this course is an amalgamation of the free and malloc functions, used to resize chunks. And you can pass it an existing chunk followed by the new size you want it to be. And programmers may be unaware that passing a size value of 0 to realloc is often an implicit free operation. This can lead to double freeze, which is exactly what happened in an Android GIF parsing library last year. What's more, heap bugs can be difficult to detect. We've seen that even when malloc's inline metadata has been corrupted, the heap can remain stable for quite some time. The GLIBC heap implementation does have a debugging mode, which makes finding bugs much easier, but again, many programmers may not be aware of its existence. So if there are lots of ways in which a heap can be corrupted, and they're difficult to detect, it stands to reason that there are plenty of undiscovered heap-related bugs out there waiting to be found. And just because we learned about the GLIBC heap during this course, that doesn't mean you can't apply what you've learned to other implementations. The reason I teach GLIBC heap exploitation specifically is because it's one of, if not the most protected, Linux heap implementation. Others like JEmalloc or gmalloc, which is used in Android devices, often don't have so much as a double free mitigation, so your knowledge is transferable. At time of recording, HeapLAB Part 2 is under construction and covers some of the more recent techniques, including the Tcache dupe, the House of Rabbit, and the House of Corrosion. Lastly, if you have time, please leave a review, it really helps. Now, go exploit some heap bugs.